Tonight, we're going to dismantle an image that has been sitting in your mind since the very first time someone showed you the solar system. You remember the picture, the sun at the center, the planets arranged in a neat line, looping around it in tidy ellipses, all of them sitting on the same flat plane, like beads strung along an invisible page. It was in your textbooks. It was on the posters in your classroom. It was probably the first map of anything beyond Earth that you ever held in your head, and it is not wrong exactly, but it is profoundly incomplete, because that picture only shows you one slice, one thin, polished, comfortable slice of something that is not flat at all. And tonight we are going to ask the strange, simple question that almost no one ever stops to ask. What is above that diagram? What is below it? If the page is flat, what is sitting on top of the page? What is sitting underneath? It is a question so simple it almost feels silly to ask. And yet the answer turns out to be one of the most disorienting truths in modern astronomy. Because what exists above and below our solar system is not nothing. It is not empty. It is not even calm. It is vast. It is layered. It is older than the planets, larger than the galaxy, and stranger than almost anyone outside of professional astronomy has ever taken the time to explain. Above you, right now, drifting silently beyond the orbits of every planet you have ever heard of, are trillions of frozen worlds wrapped around our sun like the shell of an enormous, invisible soap bubble. Below you, that same shell continues, unbroken, in every direction at once. Beyond it, you will find a cavern of nearly empty space carved by the ghosts of supernovae that exploded long before any human being existed. Above the disk we live in, you will find ancient cities of stars, older than the Earth itself, drifting in slow, lonely orbits that have nothing to do with the planets. Higher still, you will find two enormous bubbles of energy, each one tens of thousands of light years tall, born from a violent outburst of the black hole at the heart of our galaxy. While our earliest ancestors were already walking the savannas of Africa, and surrounding all of that, above, below, and through every direction at once, sits an invisible sphere of something we still cannot name. Something 5 times more massive than every star, every planet, every cloud of gas you can see, and even that is not the largest layer. By the end of tonight, the word above will not mean what it meant to you this morning. The word below will quietly dissolve, and the flat little diagram you grew up with will look in your mind like a single grain of sand, resting on a beach you cannot see the end of, so slow your breathing. Settle in. We have a long, quiet, careful journey ahead of us tonight. Out from the page, through the silence, and into the layers most people will never know are there. And before we begin, if you find this kind of slow, deep exploration of the cosmos calming, or fascinating, or simply worth your time, a quiet like or a soft tap on subscribe really does help this channel keep growing. It is a small thing for you, but it makes a real difference for me. Then we'll go on. Now, before we leave the familiar behind, let me ask you something. When you close your eyes and picture our solar system, do you still see it flat? Like a dinner plate with the planets sliding around the rim? Most of us do. Most of us have carried that image for so many years, we have never really questioned it. So tell me in the comments below where you first saw that picture. A school book, a bedroom poster, a father pointing at the sky, because before we walk away from that image forever, we are going to step inside it one last time. We are going to look at the diagram you grew up with. And we are going to see very carefully where the lie begins. Picture it again. The image you have carried since childhood. A bright golden disk at the center glowing softly. Around it in calm concentric rings the planets. Mercury tucked in close. Venus just behind it. Then Earth, the small blue marble where you happen to be right now. Mars, rust-colored and quiet. Then a wide gap scattered with asteroids. And beyond that gap the giants. Jupiter banded and enormous. Saturn with its impossible rings, Uranus tipped on its side, Neptune distant and deep blue. And out past them all, depending on how old your diagram was, a small, defiant Pluto still clinging to its old title. Each planet sits on its own orbital ring, and every ring is drawn on the same flat surface. No planet hangs above. No planet hangs below. The whole arrangement looks like a record on a turntable or a series of ripples spreading across the surface of a still pond. It is a beautiful image. It is also, quietly, a trick. Because the moment you look at the real numbers, the diagram starts to wobble. The Earth's orbit defines the plane we call the ecliptic. It is the reference frame, the page on which we draw everything else. And almost every other planet leans just a little bit off of that page. Mercury, the innermost, leans the most. Its orbit is tilted by about 7 degrees from the ecliptic. That might not sound like much, but on the scale of the solar system, 7 degrees is enough to lift Mercury more than 10 million kilometers above the page at one part of its orbit, and dip it more than 10 million kilometers below at another. The neat little dot in your textbook diagram is actually nodding slowly, up and down, year after year, like a small boat rocking on a long, slow swell. Venus tilts a little more than 3 degrees, Mars just under 2, Jupiter barely more than 1. Saturn and Uranus and Neptune between 1/2 of a degree and just over 1.5. These are tiny numbers, and yet on the vast scale of the solar system they are real. They are not noise. They are not rounding errors. They are leaning. And then there is Pluto. Pluto's orbit is tilted by more than 17 degrees from the ecliptic, so sharply that, at certain points in its long, slow loop around the Sun, it climbs more than 1 billion kilometers above the plane of the planets. At other points, it sinks 1 billion kilometers below it. The image of Pluto sitting on the same flat record as Earth is not just simplified. It is, in a quiet way, a small fiction, and Pluto is not even the strangest case. Far beyond it, in the dim outer reaches we will visit later tonight, there are entire populations of icy worlds whose orbits tilt 20, 30, 50, even 90 degrees from the page. Some of them orbit nearly perpendicular to the planets. Some of them orbit backward the wrong way around the Sun. We will get to them. But for now, simply hold this. The solar system is not a record. It is not a turntable. It is something more like a thick, soft pancake, with edges that are softer than you have been told. Astronomers, knowing this, do not actually use the Earth's orbit as the master reference for the solar system. They use something called the invariable plane. The invariable plane is the true average. It is the plane defined by the total angular momentum of every object in the solar system, summed together. Every planet, every moon, every asteroid, every comet, every grain of dust. All of their motion added into a single great vector, perpendicular to a single ideal plane. And here is the quiet shock. The Earth's orbit, the page on which all your diagrams were drawn, is not on that invariable plane. It is tilted away from it by a little more than 1 degree. Jupiter's orbit is closer, within about 1/2 a degree. Because Jupiter is so massive and so far from the Sun, more than 60% of the entire angular momentum of the solar system belongs to Jupiter alone. Jupiter is not a planet in the diagram. Jupiter is, in a quiet sense, the conductor of the diagram. The Sun spins, the planets loop, but the rhythm, the underlying flat tendency of the whole system, that is being kept mostly by Jupiter. Let that sink in for a moment. The flatness you see in every textbook is not a property of the Sun. It is not a rule imposed from above. It is the slow, summed-up dance of every object in the system, weighted by mass, weighted by distance. And it does not quite match the orbit of your own home planet. You have been looking at the wrong page. Now you might ask, if the planets really are this close to flat, only nudged off by a few degrees here and there, why? Why a pancake at all? Why not a swarm? Why not a cloud? Why not a chaos of orbits going in every direction at once like bees around a hive? That question is the door we are about to walk through, because the flatness is not random. The flatness is a fingerprint. It is the fossil signature of how the solar system was born 4.5 billion years ago. And once you understand where the flatness comes from, you will also understand almost immediately why it cannot be the whole story. Why there have to be things above the pancake and below it. Why, in fact, there must be a second solar system hidden in plain sight that almost no one outside of astronomy ever bothers to picture. But before we follow that thread back to the beginning of everything, let me ask you something. Now that you know the planets aren't really lined up on a single flat sheet, which planet's tilt surprised you the most? Was it tiny Mercury, nodding gently above and below? Was it Pluto, swinging more than 1 billion kilometers off the page? Or was it the strange truth about Earth itself? That your own home is not the reference frame, that you are the one slightly off-center, and Jupiter is the silent timekeeper of the whole arrangement? Let me know in the comments, and take your time with it, because to understand what waits above and below this gentle pancake, we first have to go back to before the planets existed, back to a quiet, slowly spinning cloud of gas, drifting in a darker, older galaxy, beginning in absolute silence to fall in on itself. To understand why the solar system is mostly flat, we have to go back, not just a few thousand years or a few million, 4.5 billion years, to time before the Earth, before the Moon, before the Sun itself was a star. Imagine in your mind's eye a vast, dark cloud of gas and dust, light years across, thin, cold, almost completely silent, mostly hydrogen with a touch of helium and the faintest sprinkling of heavier elements: carbon, oxygen, iron. The slowly drifting ash of earlier stars that had already lived and died, and seeded the galaxy with the raw material for what would come next. This cloud is not flat. It is not a disk. It is not anything in particular yet. It is something closer to a soft, lumpy, three-dimensional fog, and like every fog of gas in the galaxy, it is spinning just a little, very slowly, almost imperceptibly, maybe a single full rotation every few million years. So slow that, if you were drifting inside it, you would not feel the rotation at all. But the rotation is real. It is there. And it is about to matter very, very much. Now imagine that, somewhere inside this cloud, something tips the balance. Perhaps a nearby star explodes as a supernova, and the shock wave from that death squeezes one corner of the cloud just a little bit denser. Perhaps two parts of the cloud simply drift into each other. Whatever the trigger, one region begins to collapse under its own gravity. The gas falls inward, the dust falls inward, and as it falls, something happens that you have already seen with your own eyes many times in your life. Think of a figure skater on the ice, arms stretched wide, spinning slowly, almost lazily, in a long, graceful turn. Now they pull their arms in tight against their chest. And what happens? They spin faster, much faster, sometimes blindingly fast. Same skater, same energy. But the moment the mass pulls in closer to the axis, the rotation accelerates. This is conservation of angular momentum, a law of the universe. Something that holds true on an ice rink, in a hurricane, in a draining bathtub, and in a collapsing cloud of gas the size of a star system. So now imagine our slowly spinning fog beginning to fall in on itself. As it shrinks, it spins faster. And faster and faster. The slow drift becomes a turn. The turn becomes a rotation. The rotation becomes a roar. And as the cloud spins faster, it begins to flatten. This is the part that almost no one explains carefully, and it is the heart of what we are trying to understand tonight. So slow down with me here. In a spinning cloud, the gas can fall freely in some directions, but not in others. Along the axis of rotation, the imaginary line going straight up and down through the middle of the spin, there is no centrifugal force pushing outward. Gas at the top can fall straight down. Gas at the bottom can rise straight up. The cloud can compress along that axis without resistance, but out at the equator of the spin, things are different. Gas at the equator is moving sideways, very fast around the axis. The faster it moves, the more it tends to fling outward. Gravity wants to pull it inward, but its own motion wants to carry it outward. The two forces find a balance, and that balance is an orbit. So the gas along the top and the bottom rains down toward the middle. The gas at the equator stays out, circling. The cloud loses its three-dimensional puffiness. It thins. It flattens. It turns from a fog into a disk. This is the protoplanetary disk, a vast, flat, slowly rotating pancake of gas and dust. At the center, the densest concentration of material collapses further and further, until its core ignites in nuclear fusion, and a new star, our sun, begins to shine for the first time. And in the disk around it, dust grains stick together. The clumps become pebbles. The pebbles become boulders. The boulders become small worlds. The small worlds collide and merge and grow until, slowly, painfully, over millions of years, the planets emerge. All of them, by their very nature, born on the same flat plane. This is why the textbook diagram looks the way it does. The flatness of the solar system is the fossilized fingerprint of a single ancient spin. But now, here is the part the textbook never tells you. Not everything in that original cloud ended up in the disk. A protoplanetary disk is not a perfectly tidy filing system. It is a violent, chaotic place. The young giant planets, Jupiter especially, did not just sit politely in their lanes. They migrated. They drifted. Their enormous gravity flung other objects around the system like billiard balls struck by a heavy cue. Some of those smaller objects fell inward into the sun. Some were ejected into interstellar space forever, and many, many more were thrown outward. Not back into the disk, but above it and below it, off the page, into every direction at once. Comets formed in the cold outer reaches of the disk, where ice could survive. Many of those comets were flung outward by Jupiter, by Saturn, by Uranus, by Neptune, in long, sweeping gravitational slingshots that sent them on highly elongated orbits. Some went almost straight up, perpendicular to the disk. Some went almost straight down. Some went sideways. The whole system was, in its early years, throwing matter out of the plane in every direction it could. And then something subtle began to happen. The galaxy itself began to push back. The Milky Way, our home galaxy, is enormous. It has its own gravity, its own tides, its own swarm of nearby stars. And on the very faint, very gentle scale of these distant outer comets, the galaxy's gravity matters. Over billions of years, those faraway comets, the ones flung into long elliptical orbits taking them tens of thousands of times farther than the Earth is from the Sun, were slowly, gently nudged by the galactic tide. Their orbits were tilted and retilted and rounded out. The original disk-like distribution they began with was smeared, slowly and patiently, into a sphere. By the time the solar system was a few 100 million years old, there were two solar systems coexisting in the same space. One of them, the one in the textbook, was flat, the planets. The asteroid belt, the inner moons, all of them more or less on the page. The other one, the one almost no one ever draws, was a sphere, a vast three-dimensional cloud of icy bodies surrounding the sun in every direction at once, above the planets, below them, behind. In front, off in all the diagonals you have never thought to look in. We did not invent that second solar system, we deduced it. Because long-period comets, the ones that take thousands or even millions of years to complete a single orbit, do not arrive at the sun from along the plane. They arrive from everywhere, from above, from below, from the constellations of the north and the constellations of the south. They come falling in toward the sun like rain that has been gathered from every part of the sky, and the only way that could possibly be true is if there is, surrounding our solar system, a vast and almost spherical reservoir of icy bodies, a cloud, a shell, an unseen second solar system perfectly hidden, sitting silently above us and below us all the time. But before we can stand at the edge of that shell and look outward, we have to walk to it. We have to leave the planets behind. We have to cross Neptune and the Kuiper Belt and the cold, scattered outer territories that almost no one has heard of. We have to meet a few quiet objects out there. Lonely worlds, far from the sun, on tilted orbits that should not exist if the solar system were truly flat. So let me ask you this before we go. If you could rewind time and float as a silent observer in the very first million years of our solar system, where would you choose to stand? Inside the disk, with the young planets growing around you, dust streaming past your eyes. Or above it, looking down on the entire spinning pancake from a quiet distance, watching the comets being flung outward into the dark. There is no wrong answer, but the question is worth holding for a moment, because now, we are going to begin the long walk outward. Past Mars, past Jupiter, past Saturn, past Uranus, past Neptune, into the cold edge of the disk where the first cracks in the flat picture begin to show themselves, and where some very strange, very small, very stubborn worlds are waiting to be named. Let us walk outward together, slowly. There is no need to hurry. The solar system is enormous, and the further out you go, the slower everything moves. Begin at the sun. Hold it in your mind as a single golden point, no larger than a grain of rice on the scale we are about to use. At that scale, the Earth is a small grain of sand, sitting just a few centimeters away. Mars is a smaller grain a little further out. Jupiter, the giant, is barely the size of a pea, sitting about 30 centimeters from the Sun. Saturn, with its rings, sits at about half a meter. Uranus drifts at a meter. Neptune, the last of the major planets, sits about a meter and a half from the Sun. That is your familiar solar system. Everything you have ever called a planet, including Pluto when it still wore that name, fits within an arm span. Hold that image. We are about to leave it. Just past Neptune, beginning at about 30 times the Earth-Sun distance and extending out to about 50, lies a wide, donut-shaped region called the Kuiper Belt. It is not a single belt. It is more like a thick, soft ring of icy rubble, leftover building blocks from the formation of the planets, never quite gathered into a world of their own. We have cataloged thousands of objects out here. Astronomers estimate there are probably hundreds of thousands of bodies in the Kuiper Belt larger than 100 kilometers across. Most of them you will never hear named. A few of them you already know. Pluto, the famous one. Once the ninth planet, now a dwarf planet, but no less interesting for the reclassification. Pluto has a heart-shaped plain of nitrogen ice on its surface, mountains of water ice that rise as tall as the Rockies, and a thin, blue, hazy atmosphere that freezes onto the ground each time the dwarf planet drifts further from the Sun. Pluto has a partner, Charon, almost half its own size, locked in a slow, mutual dance. The two of them turn around a common center of gravity that lies in the empty space between them. Pluto does not orbit Charon. Charon does not orbit Pluto. They orbit each other. Then there is Eris, slightly smaller than Pluto but more massive. So massive, in fact, that its discovery in 2005 is what triggered the great reclassification debate. If Pluto was a planet, then Eris had to be a planet too. And so did several other newly discovered worlds. Astronomers, faced with a swelling list of small icy bodies, chose a new word: dwarf planet. Pluto kept its dignity. Eris took its place beside it. Then Haumea, an oblong, spinning, egg-shaped world that completes a full rotation in less than 4 hours. So fast that its own rotation has stretched it into an elongated shape, and so cold that its surface is coated in crystalline water ice, glittering faintly in the darkness. Then Makemake, named for a creation god of Easter Island. Slightly smaller than Pluto, reddish-brown, with a thin, transient atmosphere that may appear and disappear depending on its distance from the Sun. These are the named worlds of the outer disk, the ambassadors of the Kuiper Belt. And here is something quiet that you may not have noticed. They are still on the page. The Kuiper Belt as a whole is still mostly flat. It is thicker than the planetary plane, yes. It is puffier. The objects in it are tilted off the ecliptic by larger angles than the planets, sometimes by 10 degrees, sometimes by 20, sometimes by 30. But it is still recognizably a disk. It still remembers the spin of the original cloud. It still belongs, more or less, to the pancake. If we stopped here, the solar system would still look almost flat. Wider than you thought, fluffier than you thought, but flat. So let us keep going. Just beyond the Kuiper Belt, the picture begins to break. We enter a region called the scattered disk. Out here, the icy bodies are no longer riding in calm, near-circular orbits. They are on long, stretched, eccentric paths. Their closest approaches to the Sun might be just past Neptune. Their farthest reaches might be hundreds of times farther than that, and their orbits are tilted. Some of them by 40 degrees, some by 60, a few by more than 70. These are the refugees of the early solar system, the ones who were flung outward by close encounters with the giant planets billions of years ago and never settled back down. They are still moving on the trajectories that exile gave them. The most famous of these is a small, distant world called Eris, whose orbit is tilted almost 44 degrees from the ecliptic. When Eris is at its farthest from the Sun, it sits about 97 astronomical units away, almost 100 times further than Earth. Sunlight out there is so faint that the Sun would look like an unusually bright star in a dark sky. There would be no warmth on your skin. There would be no real daylight. You would walk on the surface of Eris, if such a thing were possible, under a sky permanently set to a deep, faint dusk. But Eris is not the strangest. The strangest is Sedna. Sedna was discovered in 2003, named for the Inuit goddess of the cold sea. And from the moment of its discovery, it broke the picture. Sedna's closest approach to the Sun is about 76 astronomical units, already more than twice as far out as Neptune, but its farthest point is more than 900 astronomical units away, nearly 1,000 times farther from the Sun than the Earth is. Sedna takes more than 11,000 years to complete a single orbit. 11,000 years. The last time Sedna was where it is right now, the Great Pyramids of Egypt had not yet been built. The first farmers were just beginning to plant grain in the river valleys of the Middle East. Writing did not exist, and Sedna has been on this same long, slow, lonely loop the entire time. Where does Sedna belong? It is too far out to be a true Kuiper Belt object. It is too detached from Neptune's influence to be part of the scattered disk. It does not really fit anywhere on the old map. Many astronomers now classify it as one of a tiny family of so-called detached objects. Some call it an inner Oort cloud object. Whatever you call it, Sedna is a hint, a whisper, a small, reddish, frozen messenger from a region we have not really named. And it is not alone. Astronomers have now found a handful of objects on Sedna-like orbits, bodies with perihelia far beyond Neptune. Bodies that almost certainly were not placed there by any of the planets we currently know. Some scientists suspect, and this is well into the territory of hypothesis tonight, not fact, that these distant detached worlds may have been nudged into their strange orbits long ago by a passing star, drifting close to the young solar system. Others suspect a still undiscovered ninth planet, sometimes called Planet 9, lurking far beyond Neptune on a vast, tilted orbit, gently shepherding these objects. The search continues. The question is real. The answer is not yet known. And these are exactly the kinds of clues astronomers love. Small, quiet anomalies that sit at the edge of a map and refuse to behave. But here is what matters for tonight. Whether Planet 9 exists or not, whether a passing star shaped Sedna or not, the simple fact remains. Out here beyond the Kuiper Belt, the orbits are no longer flat. The solar system is opening up. It is widening in every direction at once. The pancake is becoming a swarm. The page is being folded into 3 dimensions. And we have only walked in our scaled-down model about 3 or 4 meters from the sun, because Sedna, at its farthest, is still less than 1,000 astronomical units away, and the cloud we are about to enter, the great hidden second solar system, begins where Sedna ends and stretches outward not by 1,000 times the Earth-Sun distance, but by 100,000 times, perhaps 200,000 times, halfway to the nearest other star. If you stood on Sedna at its farthest point and looked outward into the dark, you would not see anything. You would not see the cloud. The cloud is too faint, too cold, too sparse to glow, but it is there, all around you, above, below, behind, ahead. A vast, almost spherical shell of frozen worlds, surrounding our entire solar system like an unimaginably large, dark, silent halo. The true outer edge of the sun's empire. And it is one of the strangest, loneliest places we have ever inferred the existence of. So let me ask you something. We have just walked slowly all the way out to Sedna. You have met Pluto and Eris and Haumea and Makemake. You have stood on a small red world that has not seen its current part of the sky since before humans built cities. If you were going to send one robotic explorer tonight in your name to any one of these distant worlds, which one would you send it to? The cold, blue-skied surface of Pluto, the lonely, tilted plain of Eris, the wildly spinning egg of Haumea, the crystalline, glittering pole of Makemake, or the 11,000-year orbit of Sedna. Tell me, take your time. The light from there will take hours to reach us anyway, because in just a moment we are going to keep walking, out past Sedna, out past everything you have ever called the solar system, into the cloud you have always lived inside but have never been shown, the first truly enormous structure waiting above us, below us, and on every side of us at once. So step off Sedna with me. Let go of the small, red, lonely world at our feet. Push off gently into the dark and keep going outward in the direction away from the sun. For a long while you see nothing. The sun is still there behind you, but it has shrunk to a brilliant point of light. Not a disk, not something you could shield with your hand. Just a single intense star, brighter than anything else in the sky, but no longer warm, no longer comforting. Around you, in every direction, is darkness, real darkness. The kind of darkness that has no glow on the horizon, no city lights leaking up into the air, no thin haze of atmosphere softening the void. The kind of darkness that only exists when there is nothing nearby to lift the curtain. You pass 2,000 times the Earth-Sun distance. You pass 5,000, 10,000, 20,000. And then, very gradually, almost without ceremony, you cross into a region that astronomers have known about for more than 70 years, but no human eye has ever seen. A region whose existence we inferred from comets long before we had the language to describe it. A region that surrounds you right now as you sit in your chair listening to this. In every direction at once. This is the Uit cloud, a vast, almost perfectly spherical shell of frozen worlds, wrapped around our sun like the outermost rind of an enormous fruit. We believe it begins somewhere between 2,000 and 5,000 astronomical units from the sun, in its denser inner region. We believe it extends outward to perhaps 50,000 astronomical units, in its main outer region. And some estimates push the very faint outermost edge to 100,000, perhaps even 200,000 astronomical units from the sun. At its outer fringe, you are nearly halfway to the next nearest star. Let those numbers sit for a moment. They are too large to feel. So let us shrink them down. If the orbit of Neptune were the size of a small dinner plate sitting on the table in front of you, then Sedna's farthest reach would be about a hand's width away from the edge of that plate. The Kuiper Belt would be a faint dust on the rim, and the outer Oort cloud at its full extent would be a vast, almost invisible sphere of icy bodies stretching out to a radius of about 80 meters, the length of an Olympic swimming pool, in every direction. Above the plate, below the plate, forward and backward and sideways, a sphere of pure, faint, frozen darkness enclosing your dinner plate of planets with a radius greater than a football field is long. That is what your solar system actually looks like. The disk of planets is one tiny chip of porcelain at the very center of an enormous, dark, three-dimensional cocoon. The Oort cloud, as best we understand it, is divided into two regions. The inner part, sometimes called the Hills cloud, sits closer in. From perhaps 2,000 to 20,000 astronomical units. Out here, the sun still rules. Its gravity still grips the icy bodies firmly. They orbit on long, slow, eccentric paths, but they are bound. And recent simulations suggest that the inner Oort cloud is not quite spherical. It is more like a thick, fat donut, or in some newer models, even a faint, slow spiral. The disk shape of the inner solar system, the memory of that original spinning cloud, still echoes here, faintly, like a fingerprint that has not entirely faded. The outer part is different. The outer Oort cloud, from about 20,000 astronomical units to 50,000 or more, is a sphere, a nearly perfect three-dimensional spherical shell surrounding the entire solar system. There is no preferred direction out here. There is no plane. There is no above or below. The icy bodies of the outer Oort cloud orbit the sun on enormous, lazy loops that take millions of years to complete. They drift slowly through the dark. They almost never come anywhere near the sun. They are barely bound to it at all. And there are a lot of them. We do not know the exact number. We cannot count them. We have never seen them directly. But the best estimates suggest there are roughly 1 trillion objects out there larger than a single kilometer across. A trillion. 1, followed by 12 zeros. Bodies the size of cities and small countries, drifting in deep, silent orbits in every direction around our sun. And if you count smaller objects, fragments larger than just a few hundred meters, the number rises higher still. Some estimates put the total in the many trillions. The Oort cloud is, by sheer count of objects, by far the most populous region of our solar system. And yet, its total mass is surprisingly small. The latest estimates suggest only somewhere between 1 and a few times the mass of the Earth, spread across that enormous volume. The Oort cloud is not heavy. It is sparse. Each object, on average, is millions of kilometers away from its nearest neighbor. If you were drifting inside it, you would still see nothing. You would still feel utterly alone. You would have to travel for years, perhaps decades, to encounter the next dim, dark, frozen world. The Oort cloud is not crowded. It is enormous and almost empty, and yet so vast that, even spread so thin, it contains a trillion silent travelers. Now here is the question you might be asking. If we have never seen the Oort cloud directly, how do we know it is there? The answer is simple. We see the visitors. Every so often, a comet falls inward toward the sun. Not a short-period comet, like Halley's Comet, which loops around every 75 years or so on a tilted orbit that still belongs roughly to the disk. No, the kind of comet I mean is a long-period comet. The kind that has never been seen before. The kind whose orbit, when carefully measured, traces back to an aphelion, a farthest point, of tens of thousands of astronomical units. The kind whose original orbital period is hundreds of thousands of years, or millions of years, or in some cases too long to confidently calculate at all. These comets do not come in along the plane of the planets. They come from every direction, from above the ecliptic, from below it, From the celestial north and the celestial south, from constellations the planets never visit. Some of them loop in clockwise, some counterclockwise. Some come almost vertically out of the dark, falling straight down toward the sun, swinging close, and then climbing back up into the night to be lost to us, perhaps forever. When astronomers gathered these long-period comets and traced their original orbits backward, they found something extraordinary. The aphelia, the farthest points of those orbits, cluster at distances of tens of thousands of astronomical units, and they are spread across the entire sky, not on the plane, not in a disk, everywhere, in every direction, a sphere. That sphere is the Oort cloud. And the comets are its messengers. Most of the time, those distant icy bodies sit quietly in their cold orbits, going about their endless business. But every so often, something disturbs them. A passing star slipping through the outer fringe of the cloud, its gravity nudging a few thousand cometary orbits. The gentle, ever-present tide of the Milky Way galaxy itself, gradually warping the largest orbits over millions of years. The chance encounter with a giant molecular cloud, a vast nursery of new stars drifting across the sun's path. Any of these can give a comet a nudge. Not a hard shove, just a feather touch of gravity. But out at 50,000 astronomical units, a feather touch is enough. A comet that has been orbiting the sun for 4 billion years suddenly finds its path slightly altered. Its new orbit begins to swing inward, and over the next hundreds of thousands of years it falls, slowly, 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 until eventually it drops past Neptune and Saturn and Jupiter and Mars, and we, on Earth, look up one night and see a new comet in the sky. Every long-period comet you have ever heard of, Comet Hale-Bopp, Comet Hyakutake, Comet NEOWASC, every one of them is an emissary from this dark, surrounding shell. A frozen sliver of the early solar system that has finally, after billions of years of patient drifting, come home for one brief, brilliant visit, before being either flung back out, or destroyed by the sun, or sent away on a path that will never bring it home again. Right now, as you sit and listen to this, the Oort cloud is above you. The Oort cloud is below you. The Oort cloud is to your left and to your right and in front of you and behind you. There is no direction you can look in tonight that does not eventually pass through it, and in some quiet sense, that is the true boundary of our solar system. Not Pluto, not the Kuiper Belt, not the heliosphere, the Oort cloud. The vast, dark, sparse, spherical shell of a trillion frozen worlds sitting silently around our sun. This is what is above us. This is what is below us. This is what waits in every direction at once, and almost no one ever pictures it. Now let me ask you something gentle. Knowing this, knowing that our home solar system is not really a flat little chart of planets, but a small bright disk wrapped inside a vast dark sphere of a trillion silent worlds, does that make our home feel bigger to you, or smaller? Does the cocoon feel comforting like a shell around us? Or does it feel lonely, the way deep water feels lonely when you cannot see the bottom? There is no right answer, but it is worth sitting with for a moment. Because the Oort cloud, vast as it is only the first thing waiting above and below us. Just beyond its outermost edge, the sun's grip finally lets go. Its magnetic influence fades. The solar wind cannot reach here, and we step out of the sun's empire altogether. Into a different region. A region that is not silent, not at all. A region that is windy and warm and surprisingly violent. A region that begins right where the sun's bubble ends, and that two small, ancient spacecraft, launched in the summer of 1977, have actually been into. So let us follow them. Let us follow Voyager out past the edge of the sun's reach, into the place where the solar wind dies. Step back inward with me for a moment. Out of the Oort cloud, back through the scattered disk, back past Sedna, back past Pluto, back to the planets. We are going to start one more journey outward, but this time we are going to walk at a different scale, and we are going to follow something real. Something that has actually made this trip. Not a thought experiment, not a model. A pair of small, ancient spacecraft drifting away from the sun at this very moment, carrying with them gold-plated records and the faintest echo of the human voice. In the summer of 1977, two probes lifted off from a humid launch pad in Florida. They were called Voyager 1 and Voyager 2. They were not large. Each one weighed less than a small car. Their computers were primitive, even by the standards of that era. Their cameras would be embarrassingly outclassed by the phone in your pocket today. But they were tough, and they were aimed outward. Over the next 12 years, Voyager 2 flew past Jupiter, then Saturn, then Uranus, then Neptune, sending back the first close images of all four giant planets. Voyager 1 took a faster route, swung past Jupiter and Saturn, then turned slightly upward out of the plane of the planets and began climbing into the deep silence above the ecliptic. After Neptune, neither probe had any more planets to visit, so they kept going, and going, and going. For decades, they sailed outward through the solar system, past the orbits of Pluto and Eris, deeper into the dark. And as they sailed, they carried instruments that were still measuring the environment around them. Magnetic fields, charged particles, the density of the medium they were passing through. The faint solar wind streaming from the sun. And then, in two slow, quiet moments, separated by 6 years, both spacecraft crossed an invisible line. A line that, until they crossed it, no human-made object had ever crossed. The boundary of the sun's reach. The edge of a vast, magnetic bubble that the sun has been blowing into space for as long as it has existed. A bubble we call the heliosphere. The heliosphere is the sun's true sphere of influence. Not gravitationally, that reaches much further, but magnetically, energetically. The sun is constantly pouring out a stream of charged particles, a hot wind of protons and electrons moving outward at hundreds of kilometers per second. This wind, the solar wind, carries with it the sun's magnetic field, stretching it outward into space like the petals of an invisible flower. For billions of years, the solar wind has been pushing outward in every direction, carving a great bubble out of the surrounding interstellar gas. Out where the wind finally slows to a stop, where it can push no further against the pressure of the gas outside, the bubble has a wall. That wall is called the heliopause. Inside the heliopause, you are in the sun's neighborhood. The sun's wind, the sun's magnetic field, the sun's particles. Outside the heliopause, you are in the wider galaxy, a different wind, a different field, a different sky. Voyager 1 crossed the heliopause in August of 2012. Voyager 2 crossed it in November of 2018. For the first time in human history, an object built by our hands had passed beyond the edge of the sun's bubble. We had reached interstellar space. And here is the strange thing. The heliopause is not nearly as far out as you might expect. It sits at roughly 120 astronomical units from the sun, at least in the direction we have measured it. That is only about 3 times farther out than Neptune, far closer than the Kuiper Belt's outer reaches. Vastly, enormously closer than the Oort cloud. If the Oort cloud were the size of the country you live in, the heliopause would be a small town near the very center. The sun's magnetic empire is only a small bright bubble at the heart of a much larger gravitational one. And the heliosphere is not a perfect sphere. We used to think it was. We used to draw it that way, in every diagram, a clean, round bubble around the sun. But the truth, revealed by the Voyager probes and by more recent missions like the Interstellar Boundary Explorer, is stranger. The heliosphere is moving. The whole sun, with all its planets, is sailing through the wider galaxy at around 230 kilometers per second around the galactic center, and at about 25 to 30 kilometers per second relative to the local interstellar gas. We are not standing still. We are flying. And as the heliosphere flies, it is shaped by the gas it is plowing through. On the side facing the direction of motion, the side we sometimes call the nose, the heliosphere is squashed. The interstellar gas pushes back against the solar wind, and the bubble is compressed. On the side trailing behind us, the bubble stretches outward into a long, slow, fading tail. Some recent models suggest the heliodal may extend hundreds of astronomical units behind us, a wake of solar plasma slowly dissolving into the wider darkness. The sun's bubble is not round. It is more like a slow comet, a teardrop, a faintly glowing droplet drifting through the dark. And so, above us and below us, the heliosphere flexes, not as far in those directions as it does forward, but still real. Voyager 1 actually angled itself upward, above the ecliptic plane before it crossed the heliopause. Voyager 2 went downward below the plane. The two probes crossed at different distances. Voyager 1 at about 121 astronomical units. Voyager 2 at about 119. Almost the same. But the small difference is real. The bubble above is not exactly the same as the bubble below. The shape is gently asymmetric. The interstellar wind, blowing from one direction, sculpts it as we move. Now, here is something worth sitting with. Both Voyagers today are still transmitting. As of right now, in 2026, both spacecraft are still in radio contact with Earth, though their signals are very faint, and their instruments are slowly being shut down one by one to conserve their dwindling power. Voyager 1 is currently more than 165 astronomical units from the Sun. Voyager 2 is just past 135. Both are in interstellar space. Both are sending back data from a region no other probe has ever reached. And both are aimed outward, on trajectories that will take them deeper into the galaxy, long after the last transmission from either of them goes silent. That silence is coming, by the way, probably within the next year or two. Their plutonium power sources are fading. The radio signals are growing too weak. One day, perhaps very soon, the last bit of data from a Voyager probe will arrive at Earth, and then there will be no more. But the probes themselves will not stop. They will not slow down. They will not turn around. They will keep going in absolute silence for the rest of the galaxy's existence. Voyager 1, in roughly 40,000 years, will pass within about 1.5 light-years of a small, dim star called Gliese 445 in the constellation Camelopardalis. Voyager 2, in about the same span, will drift past a star called Ross 248. Neither probe will ever stop. They will outlive the Earth. They will outlive the Sun. They will be drifting, dark and cold and silent, when the last star in the galaxy finally fades. And out there in the dark they will pass through something we have not yet talked about. Because the moment you leave the heliosphere, you do not enter true emptiness. You enter a medium. Thin, yes. Almost a perfect vacuum, yes, but not empty. The Voyager probes, the moment they crossed the heliopause, began measuring something different. A different density, a different magnetic field, a different temperature. They entered the local interstellar medium, the wider gas of our part of the galaxy, and here is where the picture again begins to shift. Because the gas just outside the heliosphere is not the typical gas of our galaxy. It is special. It is warmer than the deep voids elsewhere. It is denser than the average. It is, in fact, a small, distinct cloud of interstellar gas, a cloudlet drifting through a larger structure. And our sun, with all its planets, with its Oort cloud, with everything we have walked through tonight, is currently passing through that cloudlet. We are inside something, right now, as you listen to this. We are inside a small, warm wisp of gas, drifting through an even larger, much darker, much stranger structure that surrounds us in every direction. And the layers are about to start getting nested in ways that almost no one has been taught to picture. So before we leave Voyager behind and step out into the gas, let me ask you this. Voyager 1 and Voyager 2 will outlive everything you have ever known. They will outlive every city, every nation, every species, every story. And they each carry a small gold-plated record on the chance that one day, billions of years from now, some other mind might find them. If you could add a single sentence to that golden record in your voice, addressed to whoever might find it, what would you say? Take your time. There is no hurry. The probes will be drifting in the dark for a very, very long time, because now we are going to step out of the bubble, past the heliopause, past the very last whisper of the sun's wind, and into the warm, faint gas that the sun has only recently learned how to push aside. Step outside the heliosphere with me, past the wall where the solar wind finally dies, past the place Voyager 1 crossed in 2012 and Voyager 2 in 2018. The first thing you notice in your imagination is that nothing dramatic happens. There is no flash, no sudden change of color, no marker, no fence, no door. The transition is invisible to the eye. It is only an instrument that can tell you the air, so to speak, has changed. The particles around you are different now. They are not coming from the sun. They are coming from elsewhere, from other stars, from ancient explosions, from the slow, vast breathing of the galaxy itself. You are now in the interstellar medium, the thin gas that fills the space between the stars, mostly hydrogen with a touch of helium, a sprinkling of heavier atoms, and a faint dust of microscopic grains. By the standards of anything you have ever touched on Earth, this medium is essentially a perfect vacuum. The best vacuums we can create in laboratories on Earth are still thousands of times denser than the typical interstellar gas. And yet, on the vast scales of the galaxy, this thin gas adds up to something enormous. It is the raw material from which new stars are eventually born. It is the breath of the galaxy, and it is not uniform. In some parts of the galaxy, the interstellar medium is very thick. There are giant molecular clouds, hundreds of light years across, where hydrogen molecules cluster into cold, dark, dense regions that eventually collapse to form new stars. In other parts, the medium is moderately thin, a warm neutral gas spread evenly through space. In still other parts, the medium is incredibly hot, but so sparse that the heat is almost meaningless, plasma at temperatures of millions of degrees, but with so few particles that you could pass through it almost unaffected. We, right now, are in a very particular pocket of this medium. A small, distinct cloud of gas with its own name, a region astronomers call the local interstellar cloud, sometimes shortened simply to the LIC or the local fluff. The local interstellar cloud is a small wisp of gas, about 30 light-years across in its longest dimension. Modest by galactic standards, it is warm, around 7,000 degrees Kelvin, roughly the temperature of the surface of the sun. But it is also incredibly thin, only about 3/10 of an atom per cubic centimeter. Compare that to the air you are breathing, which has roughly 2.5 times 10 to the 19th molecules per cubic centimeter. The local cloud, the gas you would step into if you walked out the back door of the heliosphere, is, by earthly standards, indistinguishable from a perfect vacuum. And yet, by the standards of where we are about to go, it is unusually dense. Our sun is currently inside this cloud. We entered it roughly somewhere between 50,000 and 100,000 years ago. The exact date is uncertain because the boundary of the cloud is not sharp. It is a slow, soft edge, a gradient, where the density gradually changes from one region to another. Some recent studies suggest that the sun may even be near a transition zone right now, where the local cloud overlaps and mixes with a neighboring cloud called the G-cloud. We may be in both at once. We may be in neither. The truth, at this level of resolution, is that the boundaries between these little wisps of gas are blurry, and our position within them is harder to pin down than you might think. What is reasonably clear is that, On cosmic timescales, our stay in this particular cloud is short. Some analyses suggest the Sun will fully exit the local interstellar cloud within the next 1900 years or so, less than 2,000 years. By the time another civilization has risen, fallen, and risen again on Earth, our solar system will have stepped out of this cloud entirely and into a different region of gas. We are passing through, not staying. A small bright bubble of solar wind drifting through one wisp of fog on its way to the next. But here is where the picture changes again. Because the local interstellar cloud is itself sitting inside something much, much larger. A structure that defines the entire local environment of our solar system, and almost no one outside of astronomy has heard its name. It is called the local bubble, sometimes the local cavity. The local bubble is enormous, at least 1,000 light-years across in its widest direction. A vast, irregular region of space in which the interstellar medium is unusually thin, unusually hot, and unusually empty. Inside the local bubble, the gas density is roughly 1/20th of an atom per cubic centimeter. So thin that, as we said earlier, even the most extreme laboratory vacuums on Earth would feel positively crowded by comparison. And yet this thin gas is screamingly hot, around 1 million degrees Kelvin. Not warm, not even hot by any earthly definition. Plasma, charged, ionized, glowing faintly in X-rays. You are inside this bubble right now. Your house, your city, your country, your planet, the sun, the Oort cloud, the heliosphere, all of it is sitting near the center of a vast, hot, almost empty cavern carved out of the wider galaxy. And the cavern is shaped strangely. The local bubble is not a perfect sphere. It is irregular. It is narrower in the plane of the galaxy, where the surrounding interstellar gas is denser and pushes back harder. It is wider above and below the galactic plane, where the gas is thinner and the bubble could expand more easily. Many astronomers describe its shape as something like an hourglass, or perhaps a peanut, with two great lobes extending up and down out of the galactic disk, joined by a narrower waist that contains us. The bubble is taller than it is wide. We sit inside its waist. How did such a structure come to be? The story, as best we understand it, is dramatic. Roughly 10 to 20 million years ago, perhaps as recently as 14 million years ago, in two nearby young stellar clusters called the Upper Centaurus Lupus and the Lower Centaurus Crux, a series of massive stars reached the ends of their short lives. These stars, born together in a dense star-forming region, had lived fast, burned hot, and produced enormous winds. And when they died, they did not die quietly. They detonated, as supernovae, one after another, probably between 10 and 20 of them exploding over the course of millions of years. Each supernova released, in seconds, more energy than the Sun will release across its entire 10-billion-year lifetime. Each one sent out an enormous shock wave of expanding gas, sweeping up the surrounding interstellar medium like a plow pushing snow. The shock waves overlapped. They merged. They collectively carved out an enormous cavity in the gas. They blasted matter outward, leaving behind a near vacuum filled with hot, glowing plasma. That cavity is the local bubble, and we are sitting inside it. Even more remarkably, we have direct evidence of those ancient supernovae here on Earth. Not in old stories, not in archaeological records, in the rocks beneath our feet, and on the floor of the deep ocean. When a supernova explodes, it forges heavy elements in the extreme conditions of its blast. Among these is a radioactive form of iron called iron-60. Iron-60 is rare. It does not occur naturally in the inner solar system. It has a half-life of about 2.5 million years, which means that any iron-60 that exists today must have been created relatively recently, in cosmic terms, and brought to us by some external source. Beginning in the late 1990s, scientists examining samples of the deep ocean floor, of crusts of manganese that have been slowly building up at the bottom of the Pacific over millions of years, began to find faint traces of iron-60. Not much, a handful of atoms per gram, but unmistakable. The signatures could not be explained by anything happening on Earth. The most likely explanation, the one most astronomers now accept, is that this iron-60 fell out of the sky. Dust from ancient supernova explosions, drifting through space, plowed into Earth's atmosphere over the past few million years and settled gently into the ocean floor. The peaks in the iron-60 record correspond to roughly 2 to 3 million years ago, and also to a span around 5 to 7 million years ago. Both times correspond, roughly, to when the Sun was passing through regions of dense supernova debris. In other words, the ashes of the very explosions that carved the local bubble have rained down upon our planet. The dust of distant deaths is in the rocks beneath the sea. Let that sit with you for a moment. The supernovae that shaped the cavity we live in did not just create our hot, empty neighborhood. They also touched the Earth itself. Their atoms are here, in the crust, in the ocean, in perhaps some traces in the soil from which your food grows. We are not separate from the catastrophes of the wider galaxy. We are quietly built from them. And the local bubble, the hourglass we live in, extends, as we said, above and below the galactic plane. Above us right now, the bubble climbs outward through hundreds of light years of nearly empty space, before finally meeting the denser interstellar gas above it. Below us, the bubble extends downward in the same way, opening into a vast, hot, sparse cavern. Above and below the disk of the galaxy, the local bubble flares outward into two great lobes, and we are caught in the narrow throat where they meet. And here is the strange truth. Outside the local bubble, the interstellar gas is much, much denser. We are passing through a hole, a clearing in the galactic forest, a quiet patch in a much more crowded medium. If you were to step outside our bubble, the gas would slowly thicken around you. Other bubbles, carved by other supernovae, sit next to ours. The Loop 1 bubble, for instance, lies just adjacent to the local bubble, and the two appear to be in contact along a shared wall. The Sun, with us inside it, is currently drifting toward the edge of the local bubble. We will exit it eventually into a denser region of the interstellar medium. The same supernovae whose ashes lie beneath the Pacific gave us this clearing, and one day we will step out of it again into a thicker fog. Now, here is where I want you to pause for a moment and turn this image over in your mind, because we have just described two things at once. We have described where we are, and we have described how we arrived here. And both descriptions point to the same uncomfortable, beautiful truth. We are not alone. We are not standing on solid ground. We are not embedded in a still and neutral cosmos. We are drifting. We are passing through. We are moving, right now, through the slow, glowing aftermath of stars that died before any human language was spoken, and the iron from their hearts is in the bones of our planet. So let me ask you this gently. When you stand outside at night and look up into the dark and feel the air around you, the air that smells of grass or of rain or of the city you live in, does it change anything for you to know that this air, this ground, this body, all of it sits inside a vast, hot, hollow cavern carved by exploding stars? Does it feel a little less local, a little less ordinary? Or does it make you feel in some quiet way that you have always been part of something much, much larger than the small life you walk through each day? Sit with that. Because the cavity we are inside of, vast as it is, has its own strange orientation. The hourglass is not standing straight up and down. It is tilted. And we, sitting at its throat, are tilted with it in a way that does not match the galaxy at all. To understand what is truly above us and below us, we have to step back one more time. We have to leave the bubble behind. We have to climb out of the cavity, out of the gas, and out into the open expanse of the galactic disk itself. And what we find there will change, very quietly, what the words above and below can possibly mean. Pull back with me now. Pull back far enough that the local bubble shrinks to a single small region, a quiet hollow in a much larger landscape. Pull back further still, until the entire neighborhood of stars we have been calling local becomes a tiny patch, a faint speckled dust, set against the much greater architecture of the galaxy that holds us. We are inside the Milky Way. We have always been inside the Milky Way. But almost no one ever stops to really picture what that means. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across in its widest dimension, containing somewhere between 100 billion and 400 billion stars. Best modern estimates put the count at around 100 to 200 billion, though the true number is impossibly hard to pin down. The galaxy is shaped, very roughly, like a great flat disk with a thicker bulge of stars at the center, surrounded by a faint halo of older stars and dark matter that extends much further out. Across the disk, four major spiral arms of denser star formation wind outward from the center, plus a number of smaller branches and spurs. In the very middle of the galaxy, in the heart of the central bulge, sits a supermassive black hole. We call it Sagittarius A star. About 4 million times the mass of the Sun, sitting at the gravitational center of our entire galaxy, 26,000 light-years away from us. We do not orbit it like a planet orbits a star. We are not nearly close enough for that. We orbit, instead, the combined gravity of every star and every dark matter clump that lies inside our orbital radius. But Sagittarius A star sits at the rough geometric center. It is, in a quiet way, the city at the heart of the country. We are not in the center. We sit about 26,000 light-years from the galactic center, on the inner edge of one of the smaller spiral structures called the Orion Arm, or sometimes the Orion Spur. We are not in one of the great primary arms. We are in something more like a quiet suburb between two larger arms, the Sagittarius Arm closer to the galactic center, and the Perseus Arm further out. Many astronomers describe our position as a relative backwater, a peaceful neighborhood away from the most crowded star-forming regions, away from the densest concentrations of supernovae and radiation. It may not be coincidence that life on Earth has had the time it needed to develop here. We are out in the gentler outskirts. Now hold this image. The galaxy is a vast, thin, slowly spinning pancake of stars. The disk is about 100,000 light-years across, but only about 1,000 light-years thick at our distance from the center. Imagine that, for a moment, on a relatable scale. If the disk of the Milky Way were a typical extra-large pizza, the disk would be perhaps 2 centimeters thick in the middle, and the dough at the edges, where we live, less than half a centimeter thick. The galaxy is overwhelmingly flatter than it is wide. It is much closer to a sheet of paper than to a sphere. We are sitting near the middle of the dough in vertical terms, not exactly on the perfect midline. Recent measurements, refined by data from the European Space Agency's Gaia mission, place the Sun somewhere between 50 and 75 light-years above the galactic midplane right now. Above, north of the disk's center line, we are not centered, we are a little bit lifted, and we are moving. The Sun, along with everything inside the Oort cloud, orbits the galactic center at roughly 220 to 230 kilometers per second. One full orbit takes us about 225 to 250 million years. The last time we were in the same neighborhood of the galaxy we are in now, the dinosaurs had not yet evolved. Earth was in the middle of the Triassic period. The continents were arranged differently. The very first small mammals had not yet appeared. Our cosmic year is so long that, on the scale of a single human life, we do not move noticeably along it at all. But on top of that great circular orbit, the Sun does something else. Something quieter, but for our purposes tonight, something much more meaningful. The sun bobs up and down through the galactic plane. It is not a smooth, single passage. It is an oscillation. A slow, gentle, vertical wobble that carries us up out of the disk on one side, back down through the midplane, and out the other side, again and again, as we sweep around the galactic center. Each full vertical cycle takes somewhere between 50 and 70 million years, depending on which model you use and which density of mass you assume for the disk. Some recent analyses suggest the half period, the time between one crossing of the galactic plane and the next, lies somewhere between 26 and 37 million years. At our maximum excursion, we rise as much as 200 to 250 light-years above the plane. Then slowly gravity pulls us back. We slide downward, gaining speed until we cross the midplane once again and continue downward, until eventually we reach a similar maximum below the plane, and then up again, and down again. Over and over for as long as the sun has been alive, and for as long as it will continue to live. We are bobbing right now as you listen to this. We are above the plane, having most recently crossed it sometime in the past few million years. Some estimates put the most recent crossing at roughly 2 to 3 million years ago, with the sun moving upward. Our nearest ancestors had already begun walking on two legs by then. The first true members of our human family, Homo habilis, were already alive, somewhere in eastern Africa. Our species was not yet here, but our family was, and the sun was crossing the great central line of the galaxy. Now consider this. The orbit of the planets, the ecliptic plane you grew up drawing diagrams on, is not aligned with the galaxy. It is not even close to aligned. The disk of the solar system is tilted by roughly 60 degrees relative to the disk of the Milky Way. 60, 2/3 of the way from one to the other. Let that sink in for a moment. The pancake of our solar system, our textbook ecliptic, is sitting at a sharp angle to the much vaster pancake of our home galaxy. Imagine taking a small dinner plate and tilting it 60 degrees against the surface of a great flat table. That is approximately what our solar system looks like, relative to the galaxy that holds it. The local plane of the planets, in other words, has nothing to do with the local plane of the galaxy. They were not built together. They were not aligned by any shared force. The solar system was born from one specific small spinning cloud, and the orientation of that cloud was set, more or less, by chance. The galaxy spins one way. The solar system spins another. The two are simply tilted with respect to each other by 60 degrees, and they always have been, and they always will be. This has a quiet and remarkable consequence. When we here on Earth talk about above and below in our solar system, we usually mean above and below the ecliptic, north of the planets and south of them. That is one set of directions. But when astronomers talk about above and below the galaxy, they mean north and south of the galactic plane, the galactic poles, and those directions are tilted 60 degrees away from our planetary north and south. The galactic North Pole in our sky lies in the constellation Coma Berenices, near the bright star Arcturus. The galactic South Pole lies in the constellation Sculptor. Neither one is at our celestial North Pole, near Polaris. Neither one is at our solar North Pole. They are in different places entirely. You have, in other words, several different versions of up. There is up, relative to your feet. That is local and depends on where you happen to be standing on Earth. There is up, relative to Earth's rotation axis. That points roughly toward the star Polaris, the celestial North Pole. There is up, relative to the orbit of the planets. That is the ecliptic North Pole in the constellation Draco. And there is up, relative to the galaxy. That is the galactic North Pole in Coma Berenices. These four directions all disagree with one another. None of them is the true up. Each one is local to a particular structure, and as we walk outward tonight, each one of them in turn will dissolve. But for now, hold this. Above us, in the direction of the galactic North Pole, lie the upper regions of the Milky Way. Below us, in the direction of the galactic South Pole, lie the lower regions. Above and below the disk, the density of stars drops away quickly. Above and below the disk, the galaxy thins. And above and below the disk, in regions we are about to visit, there are quiet populations of older, slower, almost ghostly objects that have nothing to do with the busy planetary dance we have been describing all night. Now, I want to ask you one quiet question before we step away from this image. Right now, as you listen to me, you are on a planet that is bobbing slowly through the disk of a great spinning galaxy. Every 60 or so million years, you make a full vertical loop, above the plane, down through it, below the plane, and up through it again. Each loop takes longer than the entire age of the Rocky Mountains. Each loop is longer than the time that has passed since the first flowers appeared on Earth. You will never personally experience a full cycle. No human will. No human ever will. And yet, here you are, sitting calmly in your room, bobbing gently in the night. If you could feel this oscillation, slowed down to the rhythm of breath, what would it feel like? Would it feel like floating, like sleep, like being rocked in a cradle? Or would it just feel like the same stillness you feel right now? Take a moment with that. There is no right answer, because in just a moment, we are going to look at what lives in those regions above and below the disk, the places we rise into and fall away from on our long, slow journey, and what we find there will surprise you. Because the disk of the galaxy is not the only place stars live. Above the disk, and below the disk, in the great open spaces beyond the plane, there are stars that have been orbiting in 3 dimensions for longer than the Earth has existed. And there are clusters of them, ancient and tightly bound, that drift through the galactic halo like silent cities of light. Let me show them to you. Lift your gaze in your imagination away from the disk. If you could stand for a moment above our galaxy, hovering a few thousand light years north of the galactic plane, looking down, you would see something extraordinary. You would see the great pinwheel of the Milky Way spread out beneath you. The bulge of the central bar, glowing softly in golden light. The spiral arms, dust-laned and richly textured, sweeping outward from the center. The thin, bright disk of stars, threaded with dark filaments where new stars are still being born. You would recognize, faintly, the constellation pattern of dust and light that, from inside, we see only edge on as a milky band across our night sky. And then you would notice something quieter, something easy to miss at first. Floating above the disk, scattered seemingly at random but bound in slow gravitational orbits around the galactic center, are small bright knots of stars. They are not in the disk. They are not in the spiral arms. They are above the disk, around the disk, sometimes far below it. Each one is a tightly bound cluster of tens of thousands, sometimes millions of stars, packed so densely that, from a distance, they look like single concentrated points of golden light. We have cataloged more than 150 of them in our galaxy. There are probably more we have not yet found. They are called globular clusters, and almost everything about them is strange. Pause and hold this fact for a moment. A globular cluster is one of the oldest structures in the universe. Most of them formed somewhere between 10 and 13 billion years ago. Their stars are ancient. Many of them are older than the Earth. Some of them are older, possibly, than our galaxy itself in its current form. They were born in the chaos of the early universe, when the Milky Way was still gathering itself together from smaller pieces. And they survived. They held together. While everything else around them merged and rearranged and reshaped itself into the spiral galaxy we now live in, these compact little cities of ancient stars simply kept orbiting. A typical globular cluster contains anywhere from 10,000 to 1,000,000 stars, packed into a region only a few tens of light years across. The density of stars at the center of a globular cluster is hundreds, sometimes thousands of times greater than the density of stars in our local neighborhood. If our sun were inside a globular cluster, the nearest neighboring star would not be 4 light-years away, as Proxima Centauri is. It might be only a tenth of a light-year, or 1/100th. The closest stars could be hundreds of times closer than they are now. Imagine the night sky from a planet inside such a cluster. There would be no real darkness. The brightest stars would not be a handful of points scattered across a velvet background. They would be hundreds, even thousands of brilliant lights scattered in every direction. Some of them would be bright enough to read by. Some would cast shadows on the ground. The whole sky would glow with the soft, layered light of a city seen from above. Night would feel, in some quiet way, like dusk that never finishes falling. The globular clusters of the Milky Way orbit the galactic center, but not in the way the disk stars do. They do not glide gently around in nearly circular paths within the plane. They orbit on long, looping, three-dimensional paths that take them high above the disk on one side, dive down through it, and continue far below the plane on the other side. Their orbits are tilted at every imaginable angle. Some loop almost perpendicular to the disk. Some go around so eccentrically that their farthest excursion is more than 100,000 light-years from the galactic center. The globular cluster NGC 2419, for instance, sits about 300,000 light-years from the galactic core, an outpost so distant that some astronomers used to wonder if it was even part of our galaxy at all. Let me name a few of them. Omega Centauri, the largest globular cluster of the Milky Way. About 10 million stars, packed into a glowing ball about 150 light-years across. So massive, in fact, that many astronomers now believe Omega Centauri is not really a globular cluster at all, but the surviving core of a dwarf galaxy that was eaten by the Milky Way long ago. Its stars have a wider range of ages and compositions than a true globular cluster should have. It is, in some sense, a ghost, the heart of another galaxy beating quietly inside ours. M13, the Great Hercules Cluster. Visible to the naked eye on a dark night as a faint, fuzzy patch in the constellation Hercules. A few 100,000 stars, 22,000 light-years from Earth. In 1974, the Arecibo radio telescope in Puerto Rico beamed a famous message toward M13. A simple binary picture depicting our solar system, our species, and the structure of DNA. The message will arrive in 25,000 years at a place where the cluster will no longer be. Stars move. The cluster has drifted slightly since we aimed at it. The message will pass through empty space where M13 used to be. It is one of those small, sad, beautiful details of long-range astronomy. We can write letters, but we cannot easily get them to a moving address. 47 Tucanae, a vast, dense globular in the southern sky, containing millions of stars, and at its core, some of the most tightly packed stellar populations we have ever measured. The center of 47 Tucanae is so dense that the stars themselves occasionally collide, or come close enough for one to strip material from another, or for two to merge entirely. Each of these clusters, and dozens more, is currently sitting somewhere above or below the plane of the disk, drifting through the galactic halo on its own ancient, lonely orbit. As we in the disk slowly slide around the galactic center on our nearly flat path, these clusters loop above us and below us and around us on patterns that have nothing to do with the spiral structure we live in. They are older than the spiral. They predate it. They will outlast it. But the globular clusters are not the only ancient population above and below the disk. Beyond them, surrounding them, intermixed with them, is something even more diffuse. Something we cannot easily see, but that we have, over the past 2 decades, learned to map with extraordinary care. It is called the stellar halo. The stellar halo of the Milky Way is a thin, spread-out population of individual ancient stars, scattered throughout the volume around the disk in a roughly spherical shape, not concentrated into clusters, not bunched into associations. Just lonely, drifting, primordial stars, each on its own long, looping orbit around the galactic center. The stars of the halo are old. Most of them are between 10 and 12 billion years old. Many of them are even older than the typical disk stars. Their orbits are tilted in every direction. Some loop almost directly over the galactic poles. Some plunge through the disk at steep angles. Some travel backward, retrograde, against the rotation of the disk itself. These stars are quiet ghosts. Most of them have very few heavy elements. They are, in chemical terms, much purer than the Sun. They formed in an early universe before generations of supernovae had enriched the gas with the iron and oxygen and carbon and nitrogen that you and I are made of. To stand on a planet around a halo star, if such planets even exist, would be to stand on something built from a much more primitive material, a leaner, simpler, older universe. And many of these halo stars, perhaps most of them, did not originally form in our galaxy at all. In the last decade, thanks largely to data from the Gaia mission, astronomers have mapped the motions of millions of stars in the Milky Way's halo with remarkable precision. And what they have found is that the halo is not random. It is patterned. It contains coherent streams, long, faint ribbons of stars all moving in similar directions, with similar chemical fingerprints. These streams are the gravitational ghosts of smaller galaxies that the Milky Way devoured long ago. One of the most famous of these is the Sagittarius stream, the long, tangled remnants of the Sagittarius dwarf spheroidal galaxy. This small galaxy has been in the process of being torn apart by the Milky Way for the last several billion years. Each time it passes through the disk of our galaxy, the Milky Way's gravity strips more stars away from it. Those stars then drift along the dwarf galaxy's orbital path, forming a vast loop that wraps several times around our entire galaxy. The Sagittarius stream stretches nearly all the way around the Milky Way, above the disk on one side, below it on the other, a great looping rope of stars that used to be part of a small companion galaxy and now belongs to ours. Even more striking is something called Gaia Enceladus, sometimes called the Gaia sausage, because of the shape it makes in plots of stellar motion. About 10 billion years ago, a dwarf galaxy roughly a quarter the size of the early Milky Way collided with our young galaxy and was completely shredded. The remnants of its stars are still here in the halo. They are still moving in patterns that betray the original collision. They live among us, scattered across the halo, identifiable by their motions and chemistries even now, 10 billion years later. A significant fraction of the inner halo's stars are not Milky Way natives at all. They are descendants of a galaxy that was annihilated. Some recent estimates suggest that the Milky Way may have eaten dozens of smaller galaxies over the course of its lifetime. The halo above us and below us is, in part, a graveyard, a record of every meal our galaxy has ever taken. A faint, three-dimensional fossil bed of older, smaller systems that no longer exist on their own, but whose stars still drift quietly through the volume around the disk. So when you stand outside on a clear night and look upward, away from the band of the Milky Way, away from the dense disk, you are looking into a region that, at first glance, looks almost empty. There are a few bright stars. There are some galaxies visible in long-exposure photographs, but mostly you see darkness. And yet that darkness above your head is not empty. Above you, right now, there are ancient stars that formed 12 billion years ago, drifting on long, lonely orbits, born in galaxies that no longer exist. Above you there are globular clusters, dense glowing cities of stars, older than the Earth, swinging through the halo on slow loops. Above you, There are streams of stripped stars from devoured dwarf galaxies, winding silently through the cosmos like the residue of an ancient battle, calmly going about their post-battle motion. None of these things are visible to your unaided eye, but all of them are there right now above your head, and the same is true below your feet on the far side of the galactic plane. The halo wraps the disk in 3 dimensions. The halo is everywhere we are not. The halo is the larger volume by far. And here is the truly remarkable thing. All of these stars, all of these clusters, all of these streams are themselves only a fraction of the total mass of the region they sit in. The stars of the disk are only a small part of the galaxy's mass. The stars of the halo are an even smaller part. There is something else around us, something much, much more massive, something that does not give off light, something that we cannot see directly, but whose presence we infer from the way every star, every globular cluster, every gas cloud, every dwarf galaxy in the entire region around the Milky Way moves. Something that holds the whole structure together. Something that, by mass, is at least 5 times more abundant than every visible thing in the galaxy combined. And it surrounds us, above and below, in a sphere so vast it makes everything we have talked about tonight look small. So before we step into that invisible sphere, let me ask you something quiet. Imagine that you were born on a planet deep inside a globular cluster, 20,000 stars visible at any given moment. The nearest neighboring star perhaps a tenth of a light year away. There is no true darkness. There is only the soft, gentle, layered light of a sky packed with suns. Would you find that beautiful? Would you find it overwhelming? Would you, having grown up under such a sky, find our own sparse, lonely, mostly dark night sky strangely empty? Take a moment with that image. There is no wrong way to feel about it, because what we are about to walk into next you cannot see at all. You cannot photograph it. You cannot detect it directly. But it is the largest single thing surrounding our sun by far. And it has been here, holding us, since long before our galaxy ever found its shape. There is something else around us. Above the disk, below the disk, between the globular clusters, between the ancient halo stars, between the streams of devoured dwarf galaxies, weaving through every part of the volume we have just walked through, there is something we cannot see. Not because it is too far away. Not because it is too dim. Because it does not give off light at all. It does not glow. It does not absorb. It does not reflect. It does not radiate in the infrared or the ultraviolet or in radio waves or in X-rays or in gamma rays. Across every part of the electromagnetic spectrum that we know how to measure, it is silent. If you tried to photograph it, your image would be blank. If you tried to listen for it, your detector would be quiet. It is, by every direct measurement we have ever made, completely invisible, and yet it is there. We know it is there because everything around it moves the wrong way. Let me show you what I mean. If you take the visible mass of the Milky Way, every star, every gas cloud, every dust grain, every black hole we have ever catalogued, every planet and asteroid we know about, and you add it all together, you get a certain total mass. Around 300 billion times the mass of the Sun, give or take. From that total mass, using the laws of gravity that have been tested for centuries, you can calculate exactly how fast a star should be orbiting the galactic center at any given distance from it. Stars closer in should orbit faster. Stars further out should orbit more slowly. The orbital speed should drop off gradually as you move outward in a smooth and predictable curve. That is not what we see. When astronomers measure the actual orbital speeds of stars across the Milky Way and across thousands of other galaxies, they find something very strange. The speeds do not drop off the way they should. As you go outward through the galaxy, far past the point where the visible matter has all been accounted for, the stars and the gas continue to orbit very nearly as fast as they did closer in. The rotation curve, as astronomers call it, stays remarkably flat where it should be falling. This means that there is more mass out there. A lot more. Mass that is gravitationally tugging on those distant stars and keeping them moving fast. Mass that is not in the disk, not in the bulge, not in the globular clusters, not in the visible halo of stars. Mass that is everywhere around us but that emits no light. We call this mass dark matter. Let us be very honest about what that name actually means. Dark matter is not a thing we have directly identified. It is a placeholder, a name we have given to the missing mass, while we work out what the missing mass is actually made of. Some physicists believe it consists of an undiscovered species of particle, something called a WIMP, a weakly interacting massive particle that barely interacts with normal matter at all. Others have proposed axions, ultralight particles that would behave almost like a faint, invisible wave. Others have proposed primordial black holes, tiny black holes formed in the first instance of the universe, drifting through the galaxy as countless dark, gravitating points. And a small minority of physicists have proposed that perhaps it is not matter at all, but rather a modification of gravity itself at very large distances. We do not know which of these, if any, is correct. We have spent decades building enormous, sensitive experiments deep underground, trying to catch a single dark matter particle as it passes through the Earth. We have built detectors at the South Pole, in mine shafts in South Dakota, beneath mountains in Italy, on the surface of the moon. Almost all of them so far have come up empty. The detections we have are subtle, ambiguous, contested. The mystery is real and it is unsolved. But while we do not know what dark matter is made of, we do know, with remarkable precision, where it is. It is everywhere around the Milky Way. It surrounds the disk in a great, roughly spherical envelope that astronomers call the dark matter halo. The dark matter halo is, by every reasonable measurement, the largest single structure associated with our galaxy. It extends far beyond the visible stars, far beyond the globular clusters, far beyond even the most distant satellite galaxies that orbit the Milky Way. The visible disk of the Milky Way is about 100,000 light-years across. The stellar halo, the diffuse population of ancient halo stars we just discussed, extends to perhaps 100,000 or 120,000 light-years from the center. The globular clusters extend somewhat further. But the dark matter halo, our best estimates suggest, extends to roughly 600,000 to 1 million light-years in radius, 6 to 10 times the radius of the visible disk, 8 times by volume, much more than that. The galaxy we live in terms of mass, is overwhelmingly dark. The total mass of the Milky Way's dark matter halo, as best we can estimate it using the motions of distant globular clusters and satellite galaxies, is somewhere around 1 to 1.5 trillion times the mass of the Sun. 1 trillion. The visible Milky Way, all of it, accounts for only 1/5 to 1/10 of that. For every kilogram of star, of dust, of gas, of planet that you can see in our galaxy, there are perhaps 5 to 10 kilograms of dark matter surrounding it, holding it together, dictating how it moves. You are inside it, right now. As you sit listening to this, dark matter is passing through your body. Not in floods, not in storms, but in a thin, gentle drift. Particles of it, whatever they are, slipping through the empty spaces between the atoms of your skin, your bones, your blood. Some of those particles, depending on which model is correct, may have been here since long before the Sun formed, long before the Earth. Some of them may be remnants of the very first moments after the Big Bang, drifting through the dark matter halo for 13 billion years before passing, on their way through the small living warmth of your body. You feel nothing. There is nothing to feel. Dark matter, by its nature, almost never interacts with ordinary matter. Your atoms and its particles barely notice each other. It is as if you are made of glass, and it is made of light, and the two simply pass through one another without resistance. And yet, gravitationally, its presence shapes everything. The dark matter halo holds the disk of the Milky Way together. It is the reason our galaxy has the shape it does. It is the reason the stars move the way they do. It is the reason every globular cluster sits on the orbit it sits on. It is the reason the Sagittarius dwarf galaxy is being torn apart in the way it is. It is the reason the Magellanic Clouds, our small companion galaxies, are following the orbital paths they currently follow. Take the dark matter away and the Milky Way as we know it would fly apart. The disk would scatter, the halo would dissolve, the whole structure would unravel within a few 100 million years, and there is more. Beyond the gravitational evidence within our own galaxy, dark matter is also visible in the bending of light around distant galaxy clusters, in the temperature patterns of the cosmic microwave background, in the way galaxies are clustered across the largest scales of the universe. Every independent line of evidence points to the same conclusion. There is, in the universe, somewhere around 5 to 6 times more matter by mass than the visible matter we have ever catalogued. We are, in a quite literal sense, swimming in something we have never seen. Now let me bring this back to the question we started with tonight. What is above our solar system and what is below? You now know that above us, just past the planets, is the Oort cloud, a spherical shell of 1 trillion frozen worlds. And around the Oort cloud is the heliosphere. Around the heliosphere is the local interstellar cloud. Around that, the local bubble. Around the local bubble, the galactic disk, with us tilted at 60 degrees against it and bobbing slowly through it. Above and below the disk, the globular clusters and the stellar halo, with their ancient stars and devoured dwarf galaxies. And around all of it, in a vast, almost spherical envelope reaching far past the most distant globular clusters, is the dark matter halo. A region almost 1 million light-years across, holding everything we have talked about together with a grip that no instrument has ever been able to see. Above your head, right now, the dark matter halo extends upward, 500,000 light-years upward, maybe more. Below your feet, the same. In every direction all around you, this invisible sphere holds the galaxy. You live inside it. You have always lived inside it. The galaxy that you call home, the disk that you can faintly see as a band across the night sky, is only the brightly lit floor of a vast, dark cathedral that surrounds you on all sides. This is, by mass, the largest single thing surrounding our sun. And we have known about it, in some form, for less than a century. The first hints came in the 1930s, when Fritz Zwicky studied the Coma galaxy cluster and noticed that the galaxies there were moving far too fast for the visible mass to hold them together. He proposed that there must be additional, invisible matter holding the cluster together. He called it Dunkelmaterei, dark matter. For decades, his idea was largely ignored. It took observations in the 1970s and 80s, particularly the careful work of Vera Rubin on the rotation curves of spiral galaxies, to bring dark matter from the fringes to the very center of modern cosmology. Today, no serious model of the universe works without it. And yet, after almost a century of effort, we still do not know what it is. That is a remarkable thing to sit with. The single largest constituent of the volume around you by mass is something nobody on Earth, alive or dead, has ever directly identified. We know it is here. We can describe its distribution. We can map its halo. We can model its effects, but we have not yet held a particle of it in our hands. Now, I want to ask you something carefully. When you think about the universe, you probably think of stars and galaxies and planets and the things you can see. But knowing now that everything you can see is only the small, bright part of a much larger, darker, invisible structure that surrounds it, does that change how you feel about the universe? Does it make you feel that what you see is more precious because it is the rare visible part? Or does it make you feel that there is something quietly haunting about the dark, holding everything in place from a distance you can never touch? Or perhaps something else entirely? Sit with the question, because in just a moment we are going to see something else above and below us, something far smaller than the dark matter halo, something far younger, but something so dramatic that, even though it was discovered only about 15 years ago, it has rewritten our picture of what our galaxy has done recently. Two enormous bubbles of energy, towering above and below the heart of the Milky Way, born from a violent outburst of the supermassive black hole at the galactic center. While our earliest human ancestors were already walking the Earth, we are about to meet them. Let us return our attention to the disk for a moment. Pull back inward, away from the vast outer dark matter halo, and look once more at the bright, glittering shape of our galaxy. The pinwheel, the thin disk threaded with spiral arms, the golden bulge of stars at the center, the supermassive black hole, Sagittarius A star, sitting silently at the heart of it all. You have always been told that black hole is sleeping. That is mostly true. Most of the time, Sagittarius A star is one of the quietest supermassive black holes we know about. It accretes very little matter. It radiates very faintly. It is a sleeping giant, a 4 million solar mass core at the center of our galaxy that, for most of its existence, has done very little to draw attention to itself. But for the last 15 years, since the year 2010, astronomers have known that this is not the whole story. Because in 2010, the Fermi Gamma Ray Space Telescope, an orbiting observatory that maps the sky in the highest energy form of light, made one of the most surprising discoveries of the 21st century. It found two enormous bubbles, not asteroid-sized, not planet-sized, not even star-sized, galaxy-sized. Two vast, glowing, gamma-ray emitting lobes of energy, stretching above and below the center of the Milky Way, symmetrical about the galactic plane, each one reaching out roughly 25,000 light-years from the galactic center. Together, they form a structure shaped almost like a colossal cosmic hourglass, with Sagittarius A star at the narrow waist, and two enormous bubbles flaring upward and downward into the halo above and below the disk. These are the Fermi bubbles, and they should not be there. Let me say something about scale because the numbers are easy to misjudge. 25,000 light-years is, give or take, the same as the distance between us and the galactic center. The bubbles are essentially as tall as the Milky Way is wide. They tower over the disk. From a sufficient distance, if you could see them with your own eyes, they would utterly dwarf the spiral structure beneath them. The disk would look like a thin pinwheel sitting between two enormous glowing balloons, and it gets stranger. In 2020, an X-ray space telescope called EROSITA, mounted on a Russian-German mission to map the X-ray sky, found something else. Two even larger structures, larger in fact than the Fermi bubbles. Two enormous lobes of hot X-ray emitting plasma extending up to 14 kiloparsecs, roughly 45,000 light-years, above and below the galactic plane. Roughly the same shape as the Fermi bubbles but bigger, enclosing them, surrounding them. The EROSITA bubbles, as they came to be called, are the X-ray shell of the same outburst that produced the Fermi bubbles. The Fermi bubbles are the hot inner core, glowing in gamma rays. The EROSITA bubbles are the outer shock front, glowing in X-rays. Two structures nested, both vast, both centered on Sagittarius A star, both extending in a near-symmetrical hourglass above and below the disk. If you were to draw them to scale, with the entire Milky Way included, the bubbles would not be a small detail. They would be the dominant feature. The disk, the spiral arms, the central bulge, everything we usually focus on, would all sit inside a single great cosmic balloon, with another balloon nested inside it, and Sagittarius A star at the very center. So how did these bubbles come to be? The most widely accepted explanation, supported by multiple lines of evidence, is that the bubbles were created by a single dramatic event, an outburst from the central black hole. Roughly 2.5 to 3 million years ago, perhaps as recently as 2.6 million years ago, Sagittarius A star did something it normally does not do. It fed. Whether a star wandered too close, or a clump of gas fell inward, or some other source of fuel became available, we cannot say with full certainty. But for a brief period, perhaps as little as 100,000 years, our central black hole became active. It pulled in matter at a far higher rate than usual, and as it fed, it produced enormous outflows. Jets, probably narrow and powerful, channeled along the black hole's spin axis, together with a great wind of hot plasma streaming outward from its accretion disk. These outflows pushed upward and downward, perpendicular to the galactic plane in the direction of least resistance. They blasted through the surrounding gas, carrying with them cosmic rays, magnetic fields, hot plasma, and enormous energy. They inflated, like two great balloons being filled from a single source, on either side of the galactic disk. And there they remain today, glowing faintly in gamma rays and X-rays, still slowly expanding, still cooling, still spreading outward into the surrounding halo. Recent studies have refined this picture further. In 2022, simulations by a team led by Karen Yang at the National Tsinghua University in Taiwan showed that a single jet event from Sagittarius A star, lasting roughly 100,000 years and occurring about 2.6 million years ago, could simultaneously explain the Fermi bubbles. The EROSITA bubbles and several other features astronomers had previously struggled to unify. The Fermi bubbles in this model are the cosmic ray-filled lobes that the jets inflated. The EROSITA bubbles are the shock fronts pushed outward through the surrounding gas. The microwave haze observed by the WMAP and Planck satellites is the synchrotron radiation from cosmic ray electrons spiraling in the bubble's magnetic fields. One event, several different signatures, a single ancient outburst, still echoing through our galaxy. And here, I want you to pause. 2.6 million years ago. That is not long ago on the timescale of the galaxy. The galaxy is about 13 billion years old. 2.6 million years is less than 1/50th of 1% of the galaxy's lifetime. On a cosmic timescale, it is recent. Almost yesterday. But 2.6 million years ago is also when, on the savannas of East Africa, our very early ancestors were already walking upright. The genus Homo, our genus, had only recently appeared. Homo habilis, the earliest known member of our family, was already alive, already making the first crude stone tools. Our species, Homo sapiens, did not yet exist, but our family did. The first hominins capable of pattern tool-making were already there, looking up at the same sky we look up at tonight. And the center of our galaxy, in that moment, was undergoing one of the most violent events in its entire visible history. Now, our ancestors did not know. They did not see it. The bubbles do not radiate strongly in visible light. They glow in gamma rays and X-rays and microwaves, all of which were invisible to the naked eye. The sky would have looked perfectly normal. The night sky above East Africa 2.6 million years ago looked very much like the night sky above East Africa tonight. The stars in different positions, the constellations shaped differently but otherwise familiar. Quiet, peaceful, unrevealing. And yet, while early humans were making their first stone hand axes, the heart of our galaxy was lighting up with an outburst whose afterglow still surrounds us, 3 million years later. The bubbles you live in were inflated, in some sense, in human history, not in geological history, not in cosmic history, in the human story. Our family was already on the Earth when the central black hole of the Milky Way poured its energy upward and downward into the halo, sculpting two enormous glowing lobes above and below the disk. Right now, those lobes still surround us. We sit inside them in some sense. We are at 26,000 light-years from the galactic center. The bubbles extend 25,000 light-years above and below the plane. We are at the outer edge of the structure. The bubbles do not, strictly, contain us. They tower nearby. But the immediate neighborhood of our galaxy, above and below the disk, is filled by them. If you could see in gamma rays, the sky above your head would not be empty. There would be a faint, vast, glowing dome of energy stretching upward from the galactic center, and another mirror-image dome stretching downward from below. Two enormous balloons with our galaxy in between. There is more. In 2025, a team of astronomers reported something remarkable, something that had been unexpected. Within the boundaries of the Fermi bubbles, in places that should have been filled with extremely hot, fast-moving plasma at temperatures of millions of degrees, they detected pockets of much cooler hydrogen gas, around 10,000 degrees Kelvin. By earthly standards, still very hot. But by the standards of the Fermi bubble's interior, that gas is essentially ice cubes in a furnace. It should not survive. It should have evaporated long ago. And yet there it sits, cold relative to its surroundings, suspended somehow in the chaos. We do not fully understand how. Perhaps these are pockets of gas that were swept up from the disk and have not yet been fully heated. Perhaps they are condensations that formed within the bubble itself, as cosmic rays cooled and gas reformed. Perhaps they are protected by magnetic fields that limit how quickly they can be eroded. The investigation continues, but the discovery added a new layer of strangeness to a structure that was already strange. The Fermi bubbles are not a smooth, uniform, glowing fog. They are textured, complicated, full of detail we have only just begun to see. Now, let me ask you something. When the central black hole of our galaxy erupted 2.5 million years ago, your ancestors were already alive. They walked beneath a peaceful-looking sky. They did not know that, 26,000 light-years away, an event was beginning whose afterglow would still surround the descendants of their descendants of their descendants, 3 million years later. They did not know what they were beneath. We do. And so I want to ask you, does it change anything for you, knowing that the cosmos is not the static, frozen thing it sometimes appears to be? Knowing that, even within human history, our own galaxy was dramatically violent. That the heart of the Milky Way, which now sleeps quietly, was awake and roaring while your great many times great-grandparents were sharpening their first tools. Does it make the cosmos feel more dramatic to you? Less stable? Or, in some strange way, more alive? Sit with that for a moment. Because we have now reached the outer edge of what is just above and below our own galaxy. The Oort cloud is below us. The local bubble is around us. The galactic disk holds us. The globular clusters and stellar halo float above and beneath. The dark matter halo surrounds it all. The Fermi bubbles and EROSITA bubbles tower above and below the center. And yet, we are still only at the level of the galaxy. To find the next layer, the next thing above us, and the next thing below us, we have to step out of the Milky Way entirely. We have to look at our galaxy from outside. We have to see the small group of galaxies we belong to, and the streams of gas drifting around them, and the slow, gentle dance that is about to bring us crashing into a galaxy not so different from our own. We are leaving the Milky Way behind. Step outside the Milky Way with me. Pull back far enough that the entire galaxy, all 100,000 light-years of it, shrinks to a single object. A spiral, a pinwheel, a flat, glittering disk seen edge-on or face-on, or at some quiet angle in between. From this distance, the sun is no longer visible. Earth is no longer visible. The Oort cloud, the planets, the local bubble, all of it has folded down into a single faint point of light somewhere in the outer part of one spiral arm. We are now small enough that the entire human story disappears. And from this vantage point, you can see at last that the Milky Way is not alone. Nearby, perhaps 2.5 million light-years away, is another spiral galaxy, larger than ours, brighter than ours, tilted toward us at a gentle angle, so we see its disk almost face-on but slightly turned. This is Andromeda, sometimes called M31. It is the largest galaxy in our cosmic neighborhood. With perhaps 1 trillion stars, it contains more stars than our own Milky Way. It is, by any measure, our great neighbor, and on a clear, dark night with no moon and no city lights, you can actually see it with the naked eye. A faint, fuzzy oval in the constellation Andromeda, the most distant object visible to the unaided human eye. Older than our species, older than our planet, sitting calmly in your sky every night, asking to be noticed. Beyond Andromeda lies another spiral galaxy, smaller, fainter, almost 3 million light-years from us. Triangulum, or M33, the third largest galaxy in our local cosmic family. And then, scattered around the Milky Way and Andromeda, are dozens more smaller galaxies. Some are dwarf spirals. Most are dwarf irregulars or dwarf spheroidals. Faint, sparse little clusters of stars, often containing only a few million stars apiece, gravitationally bound to either the Milky Way or to Andromeda. We now know of somewhere around 80 members of this family. There are almost certainly more we have not yet discovered. The smallest of them are barely visible at all. They are called ultra-faint dwarf galaxies, and many of them contain so few stars that, until the last decade or so, we did not realize they existed. Together, this gathering of galaxies is called the local group. It is the small cosmic neighborhood we inhabit. About 10 million light-years across, dominated gravitationally by the Milky Way and Andromeda, with everything else orbiting one or the other or, in some cases, drifting on long looping paths between the two. And now, I want you to picture something carefully. The local group is not flat. The galaxies in it are not arranged on a single plane. They float in a roughly spherical volume of space, with the Milky Way and Andromeda near the center, and the smaller galaxies arranged in a three-dimensional distribution all around them. There are some interesting patterns. Many of the satellite galaxies of the Milky Way appear to lie roughly along a single plane, a structure astronomers sometimes call the vast polar structure. Andromeda also appears to have a thin plane of satellites. These patterns are surprising and still under active study. We do not fully understand why they exist, but on the largest scale, the local group is a three-dimensional cluster: galaxies above the Milky Way's disk, galaxies below it, galaxies on every side. Above the disk of our galaxy, in particular, there are two very famous companions: the Large Magellanic Cloud and the Small Magellanic Cloud. Two small, irregular galaxies, visible from the southern hemisphere as bright, fuzzy patches in the night sky. The Large Magellanic Cloud sits about 160,000 light-years away from us, currently below the galactic plane, more or less directly beneath us in galactic terms. The Small Magellanic Cloud sits about 200,000 light-years away, in roughly the same direction. Both galaxies are slowly being torn apart by the gravity of the Milky Way. Both galaxies are leaving long, faint streams of gas behind them as they move. These streams, taken together, form a structure called the Magellanic Stream. A vast, glowing ribbon of hydrogen gas that wraps roughly halfway around the Milky Way, trailing behind the Magellanic Clouds on their current orbit. The Magellanic Stream is huge, hundreds of thousands of light-years long, containing somewhere around 2 billion solar masses of gas. It rises above the disk and curves around the Milky Way like an enormous loop of smoke around a candle. And here is something delightful, in its own quiet way. The Magellanic Stream may be feeding our galaxy. The gas in it eventually may rain down onto the disk of the Milky Way, providing raw material for future star formation. The slow death of the Magellanic Clouds, in other words, may be the slow birth of new stars yet to come. Now, look outward again. Look beyond the local group. About 50 million light-years from us lies the Virgo cluster, a much larger gathering of galaxies containing well over 1,000 of them. Massive elliptical galaxies, large spirals, dwarf galaxies, all of them swarming around a few enormous central galaxies, the most prominent being M87, a giant elliptical galaxy that famously contains the first supermassive black hole ever photographed directly by the Event Horizon Telescope. The Virgo cluster is the gravitational anchor of our neighborhood. It is so massive that everything around it, including our own local group, feels its gravitational tug. We are slowly being drawn toward it. Over the next tens of billions of years, the local group itself will likely drift in that direction, even as dark energy stretches the rest of the universe apart. But Virgo, and our local group, and many other smaller clusters and groups, are themselves part of something even larger. They are part of the Virgo supercluster, a region of space about 110 million light-years across, containing perhaps 100 galaxy groups and clusters, with the Virgo cluster as its dominant center. And the Virgo supercluster, in turn, is part of something even larger still. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper that changed our understanding of where we live. By carefully mapping the peculiar velocities of thousands of galaxies, by which I mean their motions relative to the overall expansion of the universe, they revealed that the Virgo supercluster is itself only an outlying piece of a much, much larger structure. A structure they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea, by Tully's definition, contains about 100,000 galaxies. It spans about 520 million light-years across. Its total mass is roughly 100 quadrillion solar masses. And it is defined not by a single tight gravitational core, but by the convergent motions of all the galaxies within it. Every galaxy in Laniakea, including the Milky Way, is being pulled slowly toward a common center of gravity. That center sits in a region called the Great Attractor, roughly 150 million light-years away from us, in the direction of the constellations Centaurus and Norma. You may have heard of the Great Attractor. It has the kind of name that almost sounds like science fiction. But it is real. It is the gravitational basin into which our entire local cosmic neighborhood is falling. We are sliding toward it at hundreds of kilometers per second, even now. The local group, Virgo, every nearby cluster, the entire Laniakea supercluster, drifting slowly inward toward a common gravitational low point. And yet, Laniakea is not gravitationally stable. The expansion of the universe, driven by dark energy, is faster than the gravitational pull holding Laniakea together. So while we are falling inward locally, the structure as a whole is being stretched apart on the largest scales. Recent studies have refined the boundaries of Laniakea, and some now suggest the supercluster may be even larger than originally measured, perhaps part of an even greater complex called Shapley-Laniakea. The mapping of the cosmic web, the truly large-scale structure of the universe, continues, and the picture keeps getting more refined. But here is what I want you to hold on to. Galaxies in the universe do not float randomly. They cluster, they group. They string together along enormous filaments, threads of dark matter and gas and galaxies stretching across the cosmos. The filaments meet at nodes, where superclusters form. Between the filaments lie vast, almost empty regions called voids. Some voids are hundreds of millions of light-years across, with almost no galaxies inside them at all. The whole thing, taken together, is called the cosmic web, a vast three-dimensional lattice of filaments and voids, draped across the entire observable universe. Galaxies sit along the filaments like dew on a spider's web, Most of the volume of the universe, however, is empty. Most of the universe is void. The bright matter we can see clings to a faint, web-like skeleton of dark matter, and the rest is silence. Our local group sits on the edge of a filament that runs into Laniakea. Above us, in a particular direction relative to the galactic disk, lies one of the great voids of the local universe, the local void. It is enormous. Recent measurements suggest the local void may be one of the larger voids in our part of the universe, extending for hundreds of millions of light years in some directions, with very few galaxies inside it. And here is something quietly beautiful. The local void is, in a real sense, pushing us. Voids do not gravitate like clusters do. They have less mass than the surrounding regions. So galaxies near them are gently pushed away, drifting outward, falling toward the denser filaments around the edges. We are not just being pulled toward the great attractor. We are also being pushed by the emptiness above us. We sit between pressures, between the gentle absence of the local void on one side and the great gravitational pull of the attractor on the other. There is no part of this picture that fits inside a textbook diagram. There is no flat page, there is no neat sphere. There is instead an enormous, draping, three-dimensional cobweb of structures, galaxies, filaments, voids, streams, bubbles, halos, all of it nested, all of it tilted, all of it tangled into one another at every scale we have ever measured. And tonight, you have followed it. You have followed the structure outward from the flat textbook diagram of the planets, through the spherical Oort cloud, past the heliosphere, through the local interstellar cloud, through the local bubble, through the galactic disk, past the globular clusters, and the stellar halo into the dark matter halo, out into the Fermi bubbles, and the Erosita bubbles, beyond the Magellanic clouds, out past the local group, past the Virgo cluster into Laniakea, and right up to the edge of the local void. You have traveled from a dinner plate to a 500 million light-year landscape, from a small chip of porcelain to a cosmic web, from a tidy little diagram on a school poster to a vast, layered, tangled, dimly glowing immensity. And we have not yet asked the strangest question of all. If the universe is a cosmic web draped across every direction, then what is above the web? What is below it? Take a moment with that. Because the answer, when we get to it, will quietly undo the entire question we started with tonight. It will quietly take above and below away from you and give you something far stranger and far more beautiful in their place. But before we go there, let me ask you gently, knowing now that there is a vast empty void above us, and a great gravitational basin pulling us inward, and a 500 million light-year structure called Laniakea holding us, does any part of the night sky still feel above you in the way it did this morning? Does the word still mean what it used to mean, or has it begun quietly to fall apart in your mind? Let me know what you think. There is no wrong answer, because we are about to take the last step outward, the last layer, the one that dissolves the very question we have been asking and replaces it with something gentler and stranger and more true. Let us take the final step. Pull back one last time. Pull back so far that Laniakea itself, the 500 million light-year supercluster we have just walked through, shrinks to a single faint shape. Pull back until the entire cosmic web spreads out beneath you, around you, above you, on every side. A vast, three-dimensional lattice of filaments and voids, stretching as far as any telescope has ever seen. Galaxies arranged along glowing threads, clusters glittering at the nodes, great dark voids opening between them, like holes in the weave of a fabric too large to take in. This is the structure of the universe on its largest visible scale. The cosmic web, hundreds of billions of galaxies, woven together into a three-dimensional net that fills every cubic light-year we can see. And here is the strange truth, the truth we have been quietly walking toward all night. There is no above this web. There is no below it. Let me explain what I mean. When you look at a map of the cosmic web drawn out by some sophisticated computer simulation or by careful survey data, you see what looks like a textured surface. Threads, knots, voids. It is tempting, with our human brains, to imagine that this map has an up and a down, that somewhere above the cosmic web sits an outside, a vantage point, a region we could fly out into and look back from, and that below the cosmic web sits another outside, a separate empty region on the other side. But that is not how the universe is built. The cosmic web does not sit inside a larger space. The cosmic web is the space. Every direction you can point, in every dimension you can imagine, leads into more web. There is no edge. There is no border. There is no outside. As far as any measurement has ever been able to determine, the universe simply continues in every direction with more of the same. More galaxies, more filaments, more voids, more structure scattered through more space, without end, without boundary, without edge. If you flew outward from the Milky Way in any direction at all, for as long as you wanted, you would not eventually reach a wall. You would not arrive at a ceiling. You would not poke through the back of a great cosmic membrane and find yourself standing in some external void looking back at the universe. You would simply keep finding more universe. Another galaxy, another supercluster, another filament, another void. On and on for as far as you cared to go. This is one of the quiet, profound truths of modern cosmology. The universe has no center. The universe has no edge. Every observer everywhere looking outward in any direction sees roughly the same structure, the same texture, the same average density of galaxies, the same gentle expansion. The cosmic web is, on the largest scales, the same everywhere we have ever looked. This is what astronomers call the cosmological principle, the idea that on a large enough scale, the universe is homogeneous and isotropic, the same everywhere. The same in every direction. There is no preferred location. There is no preferred direction. There is no preferred axis. There is no above. There is no below. Sit with that for a moment. Above and below were always earthly words. They were words invented by creatures who lived on a curved surface, with gravity pulling them toward one direction. Down meant toward Earth's center. Up meant away from it. The words worked beautifully here. They still work here. They are the words you use every day without thinking. You know which way is up because your inner ear tells you, because gravity tells you, because the ground is there. But the moment you leave the ground, the words begin to weaken. On the space station, astronauts have no up or down. Their inner ears get confused. They have to learn gently that the words no longer apply. Up becomes the direction your eyes are facing. Down becomes the direction your feet happen to be pointing. There is no longer a universal answer. The words become local. In the solar system, above and below got their meanings from the ecliptic. North of the planets was up. South was down. We picked a side. By the convention of the International Astronomical Union, up is the side from which the sun and the planets appear to rotate counterclockwise. That is the ecliptic north. It points roughly toward the constellation Draco, but it could have been the other way. There is no physical reason to prefer one side over the other. We chose. In the galaxy, above and below shifted again. Galactic north and galactic south are different from ecliptic north and ecliptic south. They are tilted by about 60 degrees. The poles of the Milky Way lie in Coma Berenices and Sculptor. We chose, again, by convention, that the rotation of the galaxy seen from one side would be called clockwise, and from the other counterclockwise, and the choice gave us a north and a south. The galaxy itself does not care. And now, finally, in the largest picture of the universe, the words run out entirely. There is no cosmic north. There is no cosmic south. The universe is the same in every direction. There is no privileged up anywhere in it. The word here simply has nothing to mean. It dissolves, but there is one thing I have not yet told you. One last detail that closes the loop on the journey we have been on tonight. If you look out into space carefully with the right kind of telescope, you can see in every direction at once a faint glow, a soft, gentle hum of microwave radiation. It comes from everywhere, from above, from below, from every side. It fills the sky with almost perfect uniformity. It is called the cosmic microwave background, the CMB, and it is the oldest light in the universe. The cosmic microwave background was emitted 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light could finally travel freely through space. For 13.8 billion years, that light has been traveling. It has been stretched by the expansion of the universe. It started as visible light, glowing white-hot from a younger, denser cosmos. It has been redshifted again and again as space itself has stretched, until now it arrives at us as faint, cold microwaves at a temperature of about 2.7 degrees above absolute zero. The CMB is, in a sense, the wallpaper of the universe. The faint glow of the cosmos itself, reaching us from every direction at once. Wherever you point your telescope, you see it. It surrounds us. And here is the quiet, perfect detail. The CMB is almost exactly the same in every direction, not perfectly. There are tiny ripples in it, tiny variations of 1 part in 100,000, that map the seeds of the structure that would later grow into galaxies and clusters and superclusters. Those ripples are the fossilized fingerprint of the earliest moments of the universe. But aside from those tiny variations, the CMB is uniform. Above us the same, below us the same, to every side the same, except for one feature. A subtle, beautiful feature that almost no one outside of cosmology knows about. There is a slight asymmetry. The CMB appears very, very slightly warmer in one direction and very, very slightly cooler in the opposite direction. The variation is small, about 1 part in 1,000, but it is real, and it is not telling us something about the universe itself. It is telling us about ourselves. It is telling us that we, the Sun, the solar system, the Milky Way, our local group, the whole nearby cluster, are moving through the cosmic background of radiation at roughly 600 kilometers per second, in a specific direction, toward the constellation Leo. The warm spot of the CMB sits in front of us as we travel. The cool spot sits behind us as we fly outward. This is the closest thing the universe has to a universal direction. And it is not a direction of the universe. It is a direction of our own motion. The universe itself is the same everywhere. We are the ones who happen to be moving. The asymmetry is in us, not in it. Let that sink in for a moment. We have spent the whole evening asking what is above and below our solar system. We have followed the layers outward one by one. The flat planetary disk, the Oort cloud, the heliosphere, the local bubble, the galactic disk, the stellar halo, the dark matter halo, the Fermi bubbles. The local group, the Magellanic Stream, the Virgo cluster, Laniakea, the local void, the great attractor, the cosmic web, and now we have arrived at the largest possible picture. And in that picture, above and below do not exist. The universe has no up. The universe has no down. The cosmic microwave background surrounds us in every direction, the same, again and again, in a perfect three-dimensional embrace. The only direction that means anything at this scale is the direction you happen to be moving, toward Leo in our case, 600 kilometers a second. You have, in some sense, been chasing a question all night that does not have an answer, not because the question is bad, but because the question is human. Above and below are gifts from Earth. They are gifts from gravity. They are gifts from a body that evolved on the surface of a single small planet where up and down were obvious. The cosmos took those words gently and dissolved them, and in their place, it gave you something else. It gave you the realization that everywhere is the center, that everywhere is the middle, that the universe does not stack. The universe nests. Every observer on every world, in every galaxy, in every cluster, in every supercluster, sees the universe the same way. Microwave glow above. Microwave glow below. Microwave glow on every side. The same warm, soft hum from every direction. The same vast cosmic web extending equally in every dimension. We are not on a stage. We are not under a ceiling. We are not standing on a floor. We are floating freely in something that has no orientation at all. We are inside the universe. Every direction is into. There is no out. So when you look up at the night sky tonight, when the day is done and the stars come out, and you tilt your head back and gaze upward into the dark, ask yourself gently whether that word still means what it meant this morning. Whether up still feels like a direction the universe agrees with, or whether it has quietly become something else. A direction of your body, a direction of your eyes, a direction of your attention. But not anymore a direction of the cosmos itself. You are not below anything tonight. You are not above anything either. You are simply inside. Inside the Oort cloud. Inside the local bubble. Inside the galactic disk. Inside the dark matter halo. Inside the Fermi bubbles. Inside the local group. Inside Laniakea. Inside the cosmic web. Inside the soft, ancient, surrounding hum of light that has been falling toward you for 13.8 billion years, from every direction at once, with no particular preference for any side. And in just a moment, we are going to walk slowly back inward from this enormous embrace all the way home, back to the porch of your house, back to your room, back to the small, warm, conscious creature sitting and listening to a voice describing a cosmos that has no above and no below. And we are going to settle, gently, into what that means for you, for the small human life you are inside of, right now. For the quiet, ordinary, miraculous business of being awake on a Tuesday, on a Thursday, on whatever night this is for you, beneath a sky that is no longer above you but all around you. So let us walk home, slowly, gently, with no hurry at all. The night is long, and you do not need to rush to the end of it. Pull back in your mind from the cosmic microwave background, from the soft, ancient hum of light surrounding you on every side, from the cosmic web with its glowing filaments and its great dark voids, from Laniakea and the great attractor and the local void, and the slow gravitational current carrying us toward a center we will never reach. Come back inward, through the Virgo cluster, past the giant elliptical galaxies at its heart, back through the long, quiet ribbon of the Magellanic Stream, looping above and below the Milky Way like an enormous slow exhalation of gas, past the local group, past Andromeda, still drifting toward us at 100 kilometers a second, past the small bright satellites we have eaten and the smaller ones we will eat someday. Come closer. Down through the Fermi bubbles, still glowing faintly in gamma rays above and below the heart of our galaxy, still carrying the energy of an outburst that lit up while our earliest ancestors were already alive, through the EROSITA bubbles surrounding them, through the vast invisible sphere of the dark matter halo, larger than anything else, holding all of it together with a grip we cannot see, closer still, through the stellar halo, with its ancient stars older than the Earth, the wandering ghosts of devoured galaxies still drifting on their billion-year orbits above and below the disk. Through the globular clusters, those tightly bound little cities of light, glowing softly in three-dimensional patterns around the galactic plane. Down into the disk itself, into the spiral arm we live in, into the small, quiet suburb between two larger arms, where new stars form slowly and the radiation is gentle, and the conditions are right for the kind of patient chemistry that, given enough time, becomes biology. Come closer. Into the local bubble, that vast hourglass-shaped cavern carved by ancient supernovae whose iron sits in the rocks beneath your feet, through its waste. Into the local interstellar cloud, that thin, warm wisp of gas we are passing through right now, that we will exit in another 1900 years, like a small boat slipping out of one patch of mist into another. Closer. Through the heliopause, where the solar wind finally dies, where the Voyager probes, two tiny patient travelers, slipped quietly out of the sun's bubble in 2012 and 2018. Through the Oort cloud, that great spherical shell of a trillion frozen worlds, surrounding our solar system in every direction, the true outer skin of the sun's empire. Closer, past Sedna, 11,000 years to a single orbit, past the scattered disk and its tilted refugees, past the Kuiper Belt with Pluto and Eris and Haumea and Makemake, past Neptune, past Uranus, past Saturn, past Jupiter, past Mars, past the Moon, and here we are, back on Earth, back in the small, warm room where you have been sitting all this time. Back inside the small, warm body listening to a voice. Back at the place we started 6 dozen layers of structure ago, the same chair, the same breath, the same single quiet listener, but the picture in your head is no longer the same. The flat diagram is gone now. The neat little ellipses, the line of planets, the page on which the textbook drew them. All of it has been peeled away, layer by layer, and shown to be only the tiniest slice of something much larger, much stranger, and much more beautiful. You know now that the solar system is not flat, that it is a small bright disk wrapped inside a vast dark sphere. You know that the sphere itself sits inside a cavern carved by supernovae, and that the cavern sits inside a tilted disk, and that the disk floats inside an invisible halo, and that the halo is wrapped in 2 enormous glowing balloons, and that the entire galaxy is itself only a single bright filament in a cosmic web, draped in 3 dimensions across a universe, with no edge, no center, no above, and no below, and you know now that you are inside all of it, not above it, not beneath it, inside. The word above was a kindness given to you by the earth, by gravity, by the simple fact that you live on a curved surface and the ground is below your feet. The word below was the same kindness in the other direction. They were beautiful words. They were useful words. They are still the right words here in this room, on this floor, in this body, where gravity points the way it points and the ground is where the ground is. But the cosmos does not stack like that. The cosmos does not have a floor. The cosmos does not have a ceiling. The cosmos is not a tower. It is not a stage. It is not a layered building with rooms one above the other. The cosmos is simply an embrace. Every direction is in. Every direction is toward. There is no out. There is no over. There is no under. You are not below the stars tonight. You are inside them. You are inside the soft surrounding glow of the cosmic microwave background, falling on you from every direction at once. Light that has been traveling for 13.8 billion years before it reached the back of your eyes. You are inside the dark matter halo, with its quiet drift of particles passing gently through your body, some of them as old as the first second of the universe. You are inside Laniakea. You are inside the local bubble. You are inside the warm wisp of the local interstellar cloud. You are inside the spherical shell of the Oort cloud. You are inside an immensity that has no preferred direction. And the immensity is not cold. It is not indifferent. It is not waiting to swallow you. It is, in some quiet sense that is hard to put into words, simply there. The way a forest is there. The way an ocean is there. The way a sky is there. It is not for you. It is not against you. It simply is. And you, the small conscious creature inside it, get to be aware of it for a little while. That is a strange and beautiful gift. That awareness is rare. We do not know how rare. We do not know if there are other minds on other worlds, on other planets, in other galaxies, in other corners of this same cosmic web, who are at this moment doing what you are doing. Lying in bed, perhaps, sitting in a quiet room, listening to a voice describe the layers above and below their own home, and discovering that those layers do not really exist as layers at all. Maybe there are many such minds. Maybe there are none and you are alone. We do not know yet, but you are awake. And you have just walked, for 2 hours, from the smallest familiar diagram you grew up with all the way to the largest picture our species has ever assembled. You have crossed from a dinner plate to a cosmic web, from a single page in a school book to an embrace that has no edges. You are still that same small, conscious creature in that same small, warm room. None of the layers we have walked through tonight have moved you, in any practical sense, even 1 centimeter. The sun is still where it was when we began. The Earth has turned, perhaps, only 15 or 20 degrees on its axis since you started listening. Almost nothing has changed, and almost everything has changed, because you cannot, easily, go back to the flat little textbook diagram now. You can look at it and recognize it and even use it, but you will know, quietly in the back of your mind, that the page on which it was drawn was always tilted, always nested, always wrapped inside something larger, and that you are not above it and not beneath it. You are inside. The night is long. There is time. The cosmos is not going anywhere. The galaxy is in no hurry. The sun will keep burning for billions of years yet. The Earth will keep turning. The cosmic microwave background will keep softly surrounding you, exactly the same temperature on every side. Nothing about your position in the universe will change between now and the moment you finally fall asleep. But something else, perhaps, will change. The way you carry the word up in your mind. The way you carry the word down. The way you imagine the space above your roof and the space beneath your floor, and what lies in those directions if you keep going long enough. You will know now that the answers are far stranger, far softer, and far more beautiful than the flat diagram ever suggested. You will know that what is above us is also below us. What is below us is also beside us. What surrounds us is enormous and quiet and old and patient, and we are inside it, always in every direction. If you have stayed with me all the way through tonight, thank you, truly. Spending 2 hours in someone's company, even through a voice in your ear, is not a small thing. It is one of the kindest things you can do for a channel like this one. If this kind of slow, deep exploration of the cosmos is something you would like more of, a quiet like, or a soft tap on subscribe, really does help. It is a small thing for you, but it makes a real difference for me. And if you have a moment, drop a single word in the comments. The name of one thing tonight that you will carry with you when you walk outside under the next clear sky. Just one. So I can know which layer of the immensity stayed with you the longest. And now settle in. Close your eyes if they are not already closed. Let your breathing slow. Let the small, warm room hold you. Let the planet hold the room. Let the Uit cloud hold the planet. Let the local bubble hold the cloud. Let the galaxy hold the bubble. Let the dark halo hold the galaxy. Let Laniakea hold the halo. Let the cosmic web hold Laniakea. Let the microwave glow surround the web. And let the immensity hold you in every direction at once, with no above and no below, in the soft, endless embrace it has been offering you since the night you were born. Sleep well under the stars, wherever they are. Good night.